At the largest scales the universe allows, far beyond individual stars or planets, astronomers observe vast islands of matter slowly taking shape. Enormous collections of gas, dust, and dark material gathering into rotating systems separated by distances so large that light itself takes millions or billions of years to cross between them. These structures are not rare features or special cases. They appear wherever the universe is old enough and quiet enough for gravity to do its work. Across the observable cosmos, their presence is consistent, patterned, and repeatable, revealed again and again by careful observation. Welcome to the Sleepy Scientist. If you enjoy settling into questions like this, you are very welcome to stay and explore them slowly. And if you feel like it, you might share where in the world you're listening from tonight. It is always grounding to know how far these calm investigations travel. For decades, astronomers have studied these structures using instruments designed to collect faint light from deep space. From ground-based observatories to orbiting telescopes, generations of measurements have traced how matter moves, gathers, and changes over cosmic time. What emerges from those observations is not a sudden event, but a process. No single moment when a galaxy simply appears. Instead, a long sequence of small changes, each governed by the same physical laws that operate closer to home. In everyday experience, structure usually requires construction, intention, or direct assembly. Yet on cosmic scales, these vast systems arise without planning or design, guided only by gravity, motion, and the slow loss of energy. This understanding did not arrive fully formed. It emerged gradually as theory and observation met each other, refined over decades through mathematics, simulation, and increasingly precise measurements of distant light. Modern research continues to sharpen this picture. New data extend observations further back in time, revealing younger and less settled systems, while confirming patterns already seen closer to the present. This exploration is not about resolving a mystery or overturning familiar ideas. It is about following a process carefully, step by step, to see how large-scale order grows naturally from simple physical conditions. What galaxy formation reveals is not disorder or randomness, but coordination unfolding over immense spans of time, a universe capable of building structure patiently, without urgency or instability. With that perspective in place, attention can now rest on how this slow assembly begins, and how the universe moves from near uniformity toward the rich structure seen today. For a brief moment in the universe's long history, nothing stood out. No stars, no galaxies, no glowing spirals or crowded clusters. Just space itself, filled almost evenly with a thin mixture of hydrogen and helium, drifting quietly in every direction. This was the universe after recombination, a period that occurred a few 100,000 years after the Big Bang, when temperatures had finally dropped enough for electrons and protons to settle into stable atoms. Before that moment, matter and light were tightly coupled, constantly scattering off one another in a hot, opaque fog. After recombination, the fog cleared. Light was suddenly free to travel, and matter was left behind to evolve on its own. What remained was astonishingly simple. Roughly 3/4 hydrogen, most of the rest helium, almost nothing else, no heavy elements, no dust, no chemistry beyond the most basic building blocks, and most striking of all, almost no structure. Measurements show that density variations at this time were tiny. Differences in matter density from one region of space to another amounted to only a few parts in 100,000. On any human scale, or even a stellar one, the universe would have appeared nearly perfectly smooth. That smoothness is not inferred from guesswork. It is directly observed. The faint afterglow of the early universe still surrounds us today as the cosmic microwave background, a bath of low-energy radiation arriving from every direction in the sky. When satellites measured this background with increasing precision, they found something remarkable. The temperature of this radiation is almost the same everywhere, differing by only tiny fractions of a degree. Those measurements were first mapped in detail by NASA missions such as COBE, and later refined with extraordinary precision by the Planck satellite. Together, they provided a kind of baby picture of the universe. Not a photograph of objects, but a map of minute variations imprinted when the universe was still young. What that picture shows is calm. There are no sharp edges, no dramatic clumps, no obvious seeds of future galaxies, just a smooth, gently mottled field of matter and radiation stretched across an expanding space. This presents an immediate puzzle. Galaxies are anything but smooth. They are dense, organized systems containing billions or even trillions of stars, bound together by gravity and shaped by motion. Spiral arms, central bulges, extended halos. All of that complexity had to come from somewhere. Yet the early universe offers almost nothing to work with. To understand why this is puzzling, it helps to think in everyday terms. If flour is scattered evenly across a table, nothing much happens. Without some unevenness to exploit, there is no obvious way for piles to form on their own. Structure usually requires contrast, difference, imbalance. And yet, on cosmic scales, imbalance was barely present. The expansion of the universe itself had already been established by this point. Observations made in the early 20th century by Edwin Hubble showed that distant galaxies are moving away from one another, with farther objects receding faster than nearer ones. This pattern is not motion through space, but the expansion of space itself, carrying matter along with it. Running that expansion backward leads naturally to a hotter, denser past. That picture, refined over decades, forms the foundation of the Big Bang cosmological model. But in this moment just after recombination, the universe was already large, already cooling, and already remarkably uniform. From a physical perspective, this uniformity is not accidental. Earlier processes, including cosmic inflation, are thought to have smoothed out irregularities by rapidly stretching space itself. Inflation explains why distant regions of the universe look so similar, even though they could never have exchanged information at ordinary speeds. The result is a universe that begins its next phase in a state of near balance. Gravity, however, does not require drama to operate. It does not need cliffs or craters. Even the smallest excess of matter is enough to exert a slightly stronger pull than its surroundings. Over short timescales, that difference is negligible. Over millions and billions of years, it becomes decisive. Still, at this early stage, nothing obvious is happening yet. Gas drifts, space expands, light streams freely for the first time. If it were possible to stand somewhere in this young universe, there would be no night sky filled with stars, no points of light at all, just darkness, broken only by a faint glow in wavelengths invisible to human eyes. Temperature differences so small they would feel identical everywhere. Motion so gentle it would be imperceptible. And yet, hidden within that calm are the conditions that will eventually give rise to everything familiar. Those tiny density variations recorded in the cosmic microwave background are real physical differences. Regions that are very slightly denser than average. Regions that are very slightly emptier. No region stands out dramatically, but none are perfectly identical either. This is the crucial detail. The universe does not start with nothing. It starts with almost nothing. and in physics, almost is often enough. The fact that galaxies exist at all tells us that these minuscule imperfections must grow. Somehow, a universe that looks nearly the same everywhere must find a way to break its own symmetry. Not violently, not suddenly, but slowly, patiently, and lawfully. This makes galaxy formation one of the more counterintuitive stories in modern science. It is not a tale of explosive construction, but of accumulation, of tiny advantages compounded over immense spans of time, of gravity quietly favoring one region over another, again and again, until differences become visible. It also places strict limits on what is allowed. If the early universe had been much smoother, structure might never have formed at all. If it had been much lumpier, matter could have collapsed too quickly, leaving a very different cosmos. The measured smoothness sits in a narrow window that permits gradual structure without runaway collapse. That balance is not poetic, it is quantitative. Observations show that the amplitude of early density fluctuations falls within a range that allows galaxies to form billions of years later, rather than immediately or not at all. Even so, nothing in this early picture resembles a galaxy in any direct sense. There are no rotating disks, no stellar populations, no central concentrations, just matter, space, and time, arranged in a way that seems stubbornly resistant to change. This is why the beginning of galaxy formation is easy to underestimate. It does not announce itself, it leaves no obvious marker, it begins below the threshold of visibility, beneath the level of intuition, in differences so small they require satellites and careful statistical analysis to detect. Yet from this near-uniform state, everything else follows, not because the universe is dramatic, but because it is persistent. Gravity never switches off, expansion never pauses, matter continues to respond, slowly amplifying what little variation exists. What looks like emptiness is, in fact, preparation. The calm that dominates this early universe is not the absence of activity, but the quiet groundwork for change. In everyday life, gravity feels decisive only when masses are large and distances are short. A dropped object falls quickly, a thrown ball arcs and lands. The effect is immediate, visible, and familiar. On human timescales, gravity announces itself clearly. On cosmic timescales, gravity behaves very differently. Here, strength matters less than persistence. Even the faintest gravitational pull, acting continuously over hundreds of millions of years, becomes impossible to ignore. A difference so small that it would never register in daily experience can reshape entire regions of the universe if given enough time. Gravity does not rush, it accumulates. In the young universe, this distinction becomes crucial. Matter was spread thinly across expanding space, and the gravitational attraction between any two nearby regions was extremely weak. If gravity had been allowed only a few seconds or even a few centuries, nothing at all would have changed. But the universe does not operate on such schedules. It offers gravity billions of years to do its work. What matters most is not how strong gravity is at any given moment, but that it never stops acting. Wherever matter is slightly denser than average, gravity pulls just a little more strongly. That pull draws in nearby material, increasing the density further. The increase is small, but it compounds. As density rises, the gravitational attraction strengthens, and the process reinforces itself. This feedback loop is known as gravitational instability. It sounds dramatic, but the reality is anything but. There is no sudden collapse, no explosive trigger. It is closer to the way water slowly pools in a shallow depression on a flat surface. The slope is barely noticeable. The movement is gentle, but given time, The low point collects more and more material simply because it is already lower than its surroundings. In the early universe, countless such shallow depressions existed. They were not valleys or pits in any literal sense, but tiny variations in density left over from the universe's earliest moments. Gravity responded to these variations patiently, favouring the slightly denser regions without ever needing a dramatic event to get started. It is important to notice what is not happening here. Matter is not rushing inward. Space is not collapsing. Nothing is tearing itself apart. Expansion continues throughout this process. Space keeps stretching, carrying matter with it. Gravity works against that expansion locally, but never cancels it outright. Instead, the universe settles into a quiet competition between two influences: expansion pulling matter apart, and gravity drawing it together where density allows. On very large scales, expansion wins. On smaller scales, gravity begins to assert itself. Understanding gravity at these scales requires a slight shift in perspective. In the early 20th century, Albert Einstein showed that gravity is not best thought of as a force acting across space, but as a consequence of space-time itself being curved by mass and energy. Objects follow the natural paths laid out by that curvature. On galactic and cosmological scales, this description becomes essential. Matter moves the way it does because space-time around it is shaped by the distribution of mass. Where there is more mass, space-time curves more strongly, and nearby matter drifts in that direction. Even so, everyday intuition remains useful. Whether described as attraction or curvature, gravity still favours regions that are already slightly heavier. The language may change, but the outcome does not. What makes gravitational instability so powerful is that it requires no special conditions beyond imbalance. There is no threshold that must be crossed before it begins, no switch that must be flipped. As long as matter exists and gravity operates, differences grow. At first, growth is extraordinarily slow. A region that is 1% denser than its surroundings does not suddenly become 2% denser. The change might take millions of years to become noticeable, but the universe is patient in a way human experience rarely demands. Over tens of millions of years, those tiny advantages accumulate. Over hundreds of millions, they become substantial. Over billions, they transform the universe. The process is self-selecting. Regions that begin slightly denser grow denser still, while under-dense regions gradually lose material. Matter drifts out of emptier areas and into fuller ones, leaving behind vast cosmic voids. This redistribution is smooth, continuous, and governed by the same simple rules everywhere. No blueprint is required. This explains why the universe does not need a dramatic origin for structure. There is no moment when galaxies are switched on. Instead, structure emerges naturally from the laws already in place, given sufficient time and a starting point that is not perfectly uniform. The scale of this process is difficult to appreciate. A difference in density measured in parts per 100,000 can, over billions of years, lead to the formation of systems containing hundreds of billions of stars. The transformation is not powered by energy injection or external influence, but by the quiet accumulation of gravitational preference. In this sense, gravity behaves less like a hammer and more like a tide. Each individual motion is subtle. Each change is incremental, but the long-term effect reshapes entire landscapes. There's also no requirement for gravity to act alone. At this stage, ordinary matter is still interacting primarily through gravity, but its behavior is already being shaped by how easily it can move, cool, and respond to compression. These details matter later. For now, Gravity is simply setting the stage. What makes this especially striking is that gravity operates identically everywhere. The same principles apply whether matter is dense or sparse, whether the universe is young or old. There is no special rule for galaxy formation. The universe does not know it is building anything at all. It is merely responding. As regions grow denser, their influence on nearby matter increases. Slight overdensities become gathering points, not because they are special, but because gravity gives no preference to symmetry. Perfect uniformity is unstable. The smallest deviation is enough to start a slow drift towards structure. This means that galaxy formation does not begin with stars, gas clouds, or visible objects. It begins with patience, with the willingness of physical law to repeat the same action endlessly, accumulating consequences that are invisible at first and unavoidable in the long run. Seen this way, gravity is not a dramatic sculptor, carving shapes with sudden force. It is a quiet organizer, gently encouraging matter to gather where it already leans, allowing structure to grow from almost nothing. Once this process is underway, something important follows. The matter that responds most strongly to gravity is not always the matter that shines. There exists mass that participates fully in this gravitational gathering while remaining invisible to light. Accepting that idea requires first understanding just how far gravity can go on its own, given time. By the time gravity has had long enough to begin amplifying tiny differences, something subtle but decisive becomes impossible to ignore. The matter that responds most strongly to gravity is not always the matter that can be seen. Galaxies, when finally observed billions of years later, move in ways that visible material alone cannot explain. Stars orbit their galactic centers far faster than expected. Gas clouds circle at speeds that should fling them outward into space. Entire galaxies within clusters move as if bound by far more mass than telescopes can account for. Again and again, motion tells a story that light does not. This discrepancy did not arise from a single strange observation. It emerged gradually as astronomers measured how galaxies rotate. In the middle of the 20th century, careful studies of spiral galaxies began to reveal a pattern. Near the center of a galaxy, stars orbit quickly, as expected. Farther out, intuition suggests that orbital speeds should decrease, much like planets in the outer solar system move more slowly than those closer to the Sun. But that slowdown never came. Stars far from galactic centers were found to move just as quickly as those much nearer in. The rotation curves were flat, not falling. Something unseen was providing additional gravitational pull, holding the galaxies together far beyond where visible matter thinned out. The most influential observational work on this problem was carried out by Vera Rubin, who systematically measured the rotation of spiral galaxies. What mattered was not advanced mathematics or speculative theory, but consistency. The same pattern appeared in galaxy after galaxy. The effect was not local, not temporary, and not explainable by dust or faint stars hiding in the outskirts. Motion itself demanded extra mass. This unseen component became known as dark matter, not because it absorbs or blocks light, but because it does not interact with light at all. It neither emits nor reflects radiation in any detectable way. Its presence is revealed only through gravity, through how it shapes the movement of everything else. Dark matter does not glow. It does not cool. It does not form stars, but it does gravitate. In the early universe, this difference matters enormously. Ordinary matter, made of atoms, interacts with radiation. It heats, cools, scatters, and resists collapse when pressure builds. Dark matter does none of these things. It responds almost exclusively to gravity. Because of this, dark matter begins to clump first. As the universe expands and gravitational instability slowly amplifies density variations, dark matter is free to fall inward without resistance from pressure or temperature. Regions that contain slightly more dark matter than average become denser more quickly, deepening their gravitational influence. Over time, these regions grow into extended structures known as dark matter halos. They are not sharp-edged objects, but broad diffuse concentrations of mass, spreading far beyond the visible boundaries of any future galaxy. These halos form the true skeleton of cosmic structure. Ordinary matter arrives later. Gas made of hydrogen and helium drifts into these gravitational wells, pulled inward by mass it cannot see. Unlike dark matter, this gas cannot simply pile up indefinitely. As it falls in, it heats. As it heats, pressure builds. Energy must be lost before further collapse can occur. But crucially, the destination already exists. Without dark matter, ordinary matter would struggle to gather at all. The early universe expands too quickly, and the gas remains too hot and diffuse for gravity alone to pull it together efficiently. Calculations show that visible matter by itself would not clump fast enough to form galaxies within the age of the universe we observe. With dark matter, the situation changes completely. Dark matter halos provide deep gravitational wells early on, giving gas a place to accumulate and cool. They act as invisible containers, holding matter in place long enough for more complex processes to unfold. In this sense, dark matter does not build galaxies directly. It makes galaxy building possible. The scale of this hidden contribution is striking. In a typical galaxy, dark matter outweighs ordinary matter by a factor of roughly 5 to 1. Most of a galaxy's mass lies outside the luminous disk, extending far into space where few stars exist. The visible galaxy is more like a bright tracer than the full structure. This explains why galaxies appear stable. Without dark matter, many observed galaxies would fly apart within a few rotations. Their stars simply move too fast to be held together by visible mass alone. Dark matter is not a convenient patch. It is a requirement imposed by observation. The idea has been tested in multiple independent ways. Galaxy rotation curves, motions within galaxy clusters, gravitational lensing, where light from distant objects is bent by unseen mass along the line of sight. Large-scale simulations of cosmic structure all point to the same conclusion. There is more mass than light reveals. Importantly, dark matter does not clump on small scales the way ordinary matter does. It does not form planets or stars or compact objects. Its halos remain smooth and extended, shaping structure without dominating local detail. This behavior matches observations remarkably well. The first galaxies therefore do not begin as collections of stars. They begin as dark matter halos, quietly assembled long before light appears. Gas follows, cooling begins, density increases. Only much later does anything shine. This ordering matters. It means that the universe's structure is laid out in advance, in a form that does not depend on chemistry, radiation, or temperature. Gravity sketches the outline first. Light fills it in later. There is a certain irony here. The most important component in the formation of galaxies cannot be photographed. It leaves no direct trace in images, yet without it, the universe would look profoundly different. Perhaps emptier, perhaps less organized, possibly unable to form the long-lived structures that allow stars, planets, and complexity to exist at all. Dark matter does not add drama to the story of galaxy formation. It removes it. It explains how structure can arise without sudden events, without improbable coincidences, and without violating known physical laws. By giving gravity more weight to work with, it allows the slow processes already underway to succeed. Once dark matter halos are in place, the universe finally has something it lacked before. Not energy, not motion, but shelter. A place where ordinary matter can gather, linger, and begin the long transformation from diffuse gas into something more recognizable. Only then does the visible universe truly begin to take shape. Once dark matter halos have quietly taken shape, something important changes. For the first time since recombination, ordinary matter is no longer drifting without destination. The universe now contains places where gravity is strong enough to hold on to gas for long periods of time. Hydrogen and helium, still making up almost all of the ordinary matter in existence, begin to fall inward toward these invisible concentrations of mass. The motion is not fast. There is no dramatic plunge. Gas drifts, curves, and gradually settles, guided by gravity that has already done much of the preparatory work. As gas enters a dark matter halo, it begins to compress. Compression matters because it brings particles closer together. When atoms crowd into a smaller volume, their random motions increase. Temperature rises. The gas heats up, not because anything external is added, but because gravitational energy is converted into thermal energy as matter falls inward. This heating creates a temporary obstacle. Hot gas resists further compression. Pressure builds, pushing outward against gravity's inward pull. If nothing else happens, the gas simply stalls, suspended in a warm, diffuse state. For galaxies to form, this heat must go somewhere. Cooling becomes the deciding factor. In astrophysics, cooling does not mean becoming cold in the everyday sense. It means losing energy. For gas in the early universe, the only way to lose energy is by emitting radiation. Atoms collide, electrons shift between energy states, and tiny packets of energy are released as light. That light escapes into space, carrying heat away with it. This process is slow, but it is relentless. Hydrogen and helium are simple elements, and that simplicity limits how efficiently they can radiate energy. They lack the complex electronic structures of heavier elements, which later generations of stars will create. As a result, early gas cools far less efficiently than gas in the modern universe. This inefficiency turns cooling into a bottleneck. Only in halos above a certain mass does gravity compress gas strongly enough for cooling to proceed at a useful pace. Smaller halos gather gas, but the gas remains too warm and diffuse to collapse further. Larger halos succeed, not because they are special, but because their gravitational pull gives cooling time to work. In this way, cooling determines which regions of the universe will host the first galaxies, and which will remain dark and empty for much longer. Modern understanding of this balance comes not only from observation, but from computation. As computing power increased in the late 20th and early 21st centuries, astrophysicists began simulating galaxy formation from first principles. Starting with dark matter distributions inferred from observations, they allowed gas to fall in, heat up, cool, and respond to gravity according to known physical laws. Research groups working with agencies such as the European Space Agency contributed to these efforts by supporting large-scale simulations and observational programs designed to test their predictions. The goal was not to force galaxies to appear, but to see whether known physics could naturally produce them. The results were reassuringly unremarkable. When dark matter halos were included, and when gas cooling was treated realistically, galaxies emerged on their own, slowly, unevenly, in some regions but not others, exactly as observation suggested they should. Without cooling, nothing progressed. With cooling that was too efficient, gas collapsed too quickly, forming unrealistic structures. The universe, it turns out, operates in a narrow but workable range where patience is rewarded. This gradual settling of gas marks a turning point. For the first time, ordinary matter begins to concentrate into regions that will eventually become visible. Still no stars, still no light in the optical sense. But density is increasing, temperatures are adjusting, motion becomes more organized. Gas does not fall straight in. It carries momentum from its earlier motions, inherited from the expanding universe itself. As it compresses, it begins to swirl, flattening slightly as angular motion becomes more important. These early motions are gentle, but they set patterns that will persist for billions of years. Importantly, not all gas behaves the same way. Some regions cool faster than others. Some halos grow large enough early on to gather significant amounts of material. Others lag behind. The universe does not produce galaxies everywhere at once. It produces them selectively. This selectivity explains why the first galaxies appear at specific times and places, rather than uniformly across space. It is not randomness. It is physics working within constraints. At this stage, the universe remains dark in any familiar sense. The gas does not glow brightly. Its radiation is spread thinly across wavelengths invisible to human eyes. But conditions are changing. Density is rising. Cooling continues. Pressure barriers weaken. The transition from invisible structure to visible matter is not marked by a single event. It is a threshold crossed gradually, as gas accumulates enough mass and sheds enough heat to allow something new to happen. What makes this moment quietly remarkable is how little intervention it requires. No new forces appear, no exotic processes are introduced. Gravity, radiation, and time are sufficient. The dark matter halos provide the shape, gas provides the substance, cooling provides the permission. Once gas can remain cool and dense for long enough, another transformation becomes possible. One that will permanently alter the universe's appearance, chemistry, and future. The stage is now set, not for sudden brilliance but for ignition. For a long time the universe had structure but no light. Gas gathered, density increased, gravity held matter in place. Yet everything remained dark in any familiar sense, with no stars to mark the growing concentrations of material. That darkness was not emptiness. It was potential, waiting for conditions to cross a very specific threshold. That threshold is reached when gas becomes dense enough, cool enough, and stable enough for gravity to take over completely. In regions where hydrogen and helium had been slowly collecting inside dark matter halos, compression continued. As atoms crowded closer together, collisions became more frequent. Temperatures rose again, but this time something different happened. Instead of halting collapse, heating accelerated it. The reason lies in scale. When gas clouds reach sufficient density, their own gravity overwhelms internal pressure. Small clumps form within larger ones, fragmenting the gas into regions that collapse independently. Each fragment grows denser, hotter, and more compact, until the core conditions become extreme. At that point, the universe produces its first stars. These earlier stars are known as population 3 stars. The name does not imply that earlier stars existed, but reflects the order in which astronomers classified stellar populations. Population 3 stars are hypothetical in the strict sense, because none have been directly observed. Their existence is inferred from theory, simulation, and the chemical fingerprints they must have left behind. They form from pristine gas. Unlike modern stars, which contain traces of heavier elements inherited from previous generations, Population 3 stars consist almost entirely of hydrogen and helium. That simplicity changes everything about how they form and how they live. Without heavier elements to help gas cool efficiently, early star-forming clouds resist fragmentation. Instead of breaking into many small stars, they tend to collapse into a few very large ones. Theoretical models suggest that population 3 stars were often tens or even hundreds of times more massive than the Sun. Bigger stars behave very differently. Their cores reach much higher temperatures and pressures. Nuclear fusion ignites quickly and runs intensely. Hydrogen is consumed at a furious rate, releasing enormous amounts of energy. These stars shine brilliantly, flooding their surroundings with radiation far more energetic than anything produced by later stellar generations. But brilliance comes at a cost. Because nuclear fuel is burned so rapidly, these stars live short lives. While the Sun will shine steadily for billions of years, a massive population 3 star may exhaust its fuel in only a few million years. On cosmic timescales, that is barely a moment. Despite their brevity, their impact is profound. Inside these stars, nuclear fusion begins to reshape the universe chemically. When hydrogen nuclei fuse, they form helium. When helium accumulates and conditions allow, it can fuse into heavier elements such as carbon and oxygen. In the most massive stars, fusion proceeds even further, building elements all the way up to iron. This process, known as stellar nuclear synthesis, is the origin of nearly every element heavier than helium found in the universe today. The carbon in organic molecules, the oxygen in water, the iron in planetary cores, all trace their ancestry back to stellar interiors. Before the first stars, none of these elements existed. Population 3 stars act as cosmic forges, creating complexity where none was possible before. When they reach the end of their short lives, many explode as powerful supernovae. In those explosions, newly formed elements are scattered outward, enriching the surrounding gas. The universe is no longer chemically uniform. This transition marks the universe's first major transformation. Darkness gives way to light. Simplicity gives way to diversity. The smooth gas of the early cosmos is permanently altered by the presence of stars. What makes this moment especially striking is that it does not require precise tuning. Once gas crosses the necessary density threshold, star formation becomes almost unavoidable. Gravity drives collapse. Nuclear physics dictates what happens next. The laws involved are the same ones operating inside modern stars, just applied under more extreme conditions. Much of what is known about these first stars comes from theoretical work by astrophysicists modelling early star formation. By combining gravity, gas dynamics, nuclear physics, and radiation transport, these models simulate how pristine gas behaves under early universe conditions. Different assumptions produce different details, but the broad picture remains consistent. Large, hot, short-lived stars form first. Although population 3 stars have never been seen directly, their fingerprints appear elsewhere. The chemical composition of extremely old stars in the Milky Way suggests that they form from gas enriched by only one or two earlier supernovae. The absence of heavy elements beyond a certain level points back to an era when only the first stars had contributed material. In this way, ancient stars act as archaeological records, preserving indirect evidence of their long-vanished predecessors. The arrival of starlight also changes how gas behaves. Radiation from these massive stars heats nearby material, ionizes atoms, and pushes gas outward. For the first time, energy flows strongly from compact objects into their surroundings. This has consequences. Star formation is no longer just a matter of gravity and cooling. It becomes a process influenced by the stars themselves. Their light alters the temperature of nearby gas. Their winds redistribute material. Their deaths inject energy and momentum into the environment. The universe becomes interactive. Another subtle but important change occurs as well. Ultraviolet radiation from the first stars begins to reionize surrounding hydrogen, reversing the calm neutrality established at recombination. Regions around early galaxies become filled with ionized gas once more, altering how radiation and matter interact on large scales. This period, known as reionization, unfolds unevenly across the universe. It is driven by the cumulative output of early stars and galaxies, gradually transforming the intergalactic medium. Although population 3 stars are few in number and fleeting in existence, their influence extends far beyond their lifetimes. They determine the chemical starting point for all later generations of stars. They shape the thermal environment of early galaxies. They mark the universe's transition from a simple, dark state to one capable of complexity. There is a quiet inevitability to this transformation. Given gas, gravity, and time, stars will form. Given stars, elements will be forged. Given elements, new kinds of structure become possible. The universe does not hesitate once this process begins. From this point onward, galaxy formation is no longer a matter of assembling matter alone. It becomes a balancing act. Stars now both create and disrupt. They illuminate and interfere. They enrich and expel. The first stars do not simply add light to the universe. They introduce regulation. What follows is not unchecked growth, but a delicate negotiation between gravity pulling inward and stellar energy pushing outward. The calm accumulation of gas now shares control with processes that actively reshape their surroundings. With the first stars ignited, the universe has crossed a line it can never return from. Once the first stars appear, galaxies stop behaving like passive collections of gas. They become active environments, shaped not only by gravity pulling inward, but by energy pushing outward from within. This interaction between stars and their surroundings is known as feedback. The word can sound mechanical, but the reality is gentle, continuous, and surprisingly orderly. Feedback does not tear galaxies apart, it regulates them. Every young star begins influencing its environment almost immediately. Even before nuclear fuel is exhausted, massive stars emit intense radiation. That light carries energy outward, heating nearby gas and changing how it behaves. Hydrogen atoms lose electrons, temperatures rise, gas that was once cooling and settling becomes warmer and more resistant to collapse. At the same time, stars produce stellar winds. These are steady outflows of particles streaming away from the stellar surface at high speeds. They are not explosive events, but persistent ones, more like a strong breeze than a sudden blast. Over time, these winds carve out cavities in surrounding gas, redistributing material across the young galaxy. Then come the supernovae. When a massive star reaches the end of its short life, nuclear fusion can no longer support its core. Gravity takes over, and the star collapses inward before rebounding in a powerful explosion. In a single event, enormous amounts of energy are released, along with newly forged elements. Supernovae are dramatic on stellar scales, but even here, their role is not simply destruction. The energy they release heats nearby gas, stirs it, and spreads heavy elements through the surrounding medium. Dense regions may be disrupted, but others are compressed, creating new pockets where star formation can resume later. Feedback is not a stop sign, it is a pause button. What matters most is timing. If gas were allowed to collapse without interruption, galaxies would convert nearly all their available material into stars very quickly. The result would be bright but short-lived systems, exhausting their fuel early and leaving little behind. Observations show that this does not happen. Galaxies form stars slowly over billions of years. Even the most active star-forming galaxies convert only a small fraction of their gas into stars at any given time. Feedback is the reason. By heating gas and increasing pressure, feedback prevents large-scale collapse from proceeding unchecked. Warm gas resists gravity more effectively than cool gas. Ionized gas behaves differently from neutral gas. Material pushed outward by winds and explosions may take millions of years to cool and settle again. In this way, feedback introduces a natural rhythm. Periods of star formation are followed by quieter phases. Activity ebbs and flows rather than racing ahead. This pattern is not speculative, it is observed directly. Images captured by the Hubble Space Telescope reveal star-forming regions filled with glowing gas, dark dust lanes, and expanding bubbles carved by stellar winds. These structures show feedback in action. Bright clusters of young stars sit beside evacuated cavities, where gas has been pushed aside by radiation and explosions. Rather than uniform brightness, galaxies display patchwork patterns. Some regions blaze with activity, others lie dormant. Feedback creates this unevenness, ensuring that star formation proceeds locally rather than globally. This self-regulation solves a major problem in galaxy formation. Without feedback, theoretical models predict galaxies that are far too massive and far too efficient at forming stars. With feedback included, simulations begin to resemble real galaxies, with realistic star formation rates and extended lifetimes. The effect is especially important in young galaxies. Early stars tend to be massive and energetic, making their influence particularly strong. A relatively small number of stars can heat and stir gas across large regions, delaying further collapse and shaping the galaxy's evolution. Feedback also explains why galaxy growth is sensitive to environment. Smaller galaxies, with weaker gravitational pull, are more easily affected by stellar energy. Gas can be heated or even pushed out entirely, slowing star formation dramatically. Larger galaxies with deeper gravitational wells retain more of their gas and can sustain activity over longer periods. This difference helps explain why the universe contains a wide range of galaxy types. Some are rich in gas and actively forming stars. Others are quiet and depleted. Feedback does not enforce uniformity. It allows diversity to emerge. Another important role of feedback is mixing. When supernovae spread heavy elements into surrounding gas, they enrich regions that were previously pristine. Later generations of stars form from this enriched material, changing their properties. Cooling becomes more efficient. Fragmentation increases. Star formation shifts towards smaller, longer-lived stars. In this sense, feedback connects generations. The first stars alter the conditions for the second influence the third. Over time, galaxies become chemically and structurally more complex, not through sudden transitions but through accumulated interaction. Feedback also operates across scales. Energy injected locally can influence gas far beyond the immediate vicinity of a star cluster. Hot gas can rise into a galaxy's halo, forming fountains that later rain material back down. This circulation redistributes matter, smoothing out extremes while preserving overall structure. Importantly, feedback does not erase the work gravity has done. Dark matter halos continue to anchor galaxies. Gravity continues to pull inward. Feedback simply slows the process enough to prevent it from running away. The balance between gravity and feedback is delicate. Too little feedback, and galaxies burn too brightly too fast. Too much, and star formation is suppressed almost entirely. Observations suggest that real galaxies sit comfortably between these extremes. This balance is not tuned by design. It emerges naturally from the physics involved. The energy output of stars depends on their mass. The response of gas depends on its density and temperature. Gravity responds to total mass. The interaction settles into a stable pattern. Even humor finds a place here, if only gently. Galaxies behave less like fireworks and more like cautious cooks, turning up the heat just enough to keep things simmering without boiling dry. As feedback continues, young galaxies develop character. Their star formation histories diverge. Some experience bursts followed by lulls. Others settle into steady, long-term production. None follow a single script. This complexity marks a turning point. Galaxy formation is no longer just a story of matter gathering under gravity. It becomes a story of interaction, response, and moderation. The universe has introduced its first internal checks and balances. From this point onward, building a galaxy is not simply about how much material is available, but about how that material is allowed to behave. Gravity still sets the direction. Feedback sets the pace. Together they ensure that galaxies grow not as sudden monuments, but as long-lived systems, capable of evolving quietly over billions of years. As galaxies grow more complex, their centers begin to matter in a new way. Not because something dramatic suddenly appears, but because mass continues to drift inward, guided by gravity and shaped by earlier events. Over time, many galaxies develop dense central regions where matter collects more efficiently than elsewhere. At the heart of most large galaxies sits an object that is both ordinary in cosmic terms and deeply unfamiliar in human ones: a supermassive black hole. These black holes are not rare exceptions. They appear to be a common feature of galaxy formation itself. Wherever astronomers can measure stellar motions near galactic centers with sufficient precision, the same pattern emerges. Stars orbit as if responding to an enormous concentration of mass packed into a very small region. In the Milky Way, that central object is known as Sagittarius A star. Careful observations of stars moving around this point show them following tight, rapid orbits, some completing a full circuit in only a few decades. The only plausible explanation is a compact object containing millions of times the mass of the Sun. What matters for galaxy formation is not how strange black holes are, but how predictable they turn out to be. Supermassive black holes do not form in isolation, nor do they arrive late as cosmic afterthoughts. Evidence suggests that their growth is closely tied to the growth of their host galaxies. As gas falls toward the center of a young galaxy, some of it feeds star formation, while some spirals further inward, eventually reaching the region dominated by the black hole's gravity. Growth on both fronts proceeds together. A black hole increases in mass by accreting surrounding material. Gas drawn too close heats up as it accelerates, forming a rotating disk around the black hole before crossing the final boundary. Friction within this disk converts gravitational energy into heat and radiation, producing enormous luminosities in a relatively small volume. When this process becomes especially intense, the galaxy hosts what is known as an active galactic nucleus. Despite the name, nothing explodes or switches on suddenly. Activity reflects how much material is available and how quickly it is falling inward. Active galactic nuclei can outshine all the stars in their host galaxies combined. Yet this brilliance is not permanent. It depends on supply. When gas becomes scarce or is heated and pushed away, activity subsides. Observations and theoretical work suggest that these active phases are intermittent. Black holes grow in episodes, not continuously. Galaxies, meanwhile, experience bursts of central activity interspersed with longer periods of quiet. This coupling has measurable consequences. Across many galaxies, astronomers find a striking relationship between the mass of the central black hole and the properties of the surrounding galaxy, particularly the mass and motion of stars in the central bulge. The correlation is too consistent to be accidental. It suggests that black holes and galaxies regulate one another as they grow. Understanding this relationship has been a major focus of research groups, such as the Max Planck Institute for Extraterrestrial Physics, where long-term observational campaigns and theoretical modelling have helped clarify how central black holes interact with their environments. One of the key roles black holes play is energetic rather than gravitational. While their direct gravitational influence is confined to the central region, the energy released during accretion can affect gas far beyond that immediate vicinity. Radiation from an active nucleus heats surrounding material. Powerful outflows and jets can push gas outward, sometimes extending thousands of light years from the center. This energy input alters how easily gas can cool and collapse into new stars. Once again, the theme is regulation rather than destruction. If too much gas collects at the center too quickly, black hole activity intensifies, heating or expelling nearby material. This reduces the fuel supply, calming both star formation and black hole growth. When activity wanes, gas can settle again, allowing the cycle to continue. This feedback loop mirrors, on a larger scale, the stellar feedback already shaping young galaxies. Stars regulate their surroundings locally. Black holes influence conditions across entire galactic centers. The result is uneven growth. Some galaxies experience strong central activity early on, slowing star formation in their cores. Others remain relatively quiet, forming stars steadily for longer periods. Over billions of years, these differences contribute to the wide variety of galaxy types seen today. Importantly, black holes do not dominate galaxies. Despite their mass, even a supermassive black hole accounts for only a tiny fraction of a galaxy's total mass. Dark matter remains the primary gravitational framework. Stars and gas make up most of the visible structure. Black holes matter because of efficiency, not size. By converting in falling mass into energy so effectively, they exert influence far beyond their immediate surroundings. They shape temperature, pressure, and motion in regions where stars alone would be insufficient. This influence is most pronounced in the dense centers of galaxies. Before large-scale shapes such as disks and ellipticals fully settle, central regions act as control points, where small changes can have wide-reaching effects. There is a tendency to treat black holes as dramatic endpoints, cosmic drains from which nothing returns. In galaxy formation, they are better understood as participants. They grow because galaxies grow. They act because material flows inward. They quiet down when conditions change. Their behavior follows from the same physical laws governing everything else in the universe. Gravity draws matter inward. Motion redistributes energy. Radiation carries energy away. Nothing exotic is required. Seen this way, supermassive black holes fit naturally into the broader story of galaxy evolution. They add depth to galactic centers without overshadowing the slower, larger-scale processes unfolding around them. They are not the authors of galaxy formation, but they are attentive editors, adjusting the pace and emphasis as the story develops. With central regions now shaped by both stars and black holes, galaxies gain an internal structure that will influence how they rotate, collide, and evolve over time. The groundwork is laid not only for growth, but for form. What emerges next is not just more mass, but recognizable shape. As gas continues to settle inside growing galaxies, another quiet influence becomes increasingly important. Not gravity pulling inward, and not energy pushing outward, but motion carried over from the universe's earlier state. Nothing in the universe begins at perfect rest. Even in the early cosmos, matter was never motionless. Tiny sideways movements existed alongside the general expansion of space. These motions were small, almost negligible at first, but like everything else in galaxy formation, they mattered once time was allowed to do its work. This inherited motion is known as angular momentum. The term can sound abstract, but the idea behind it is simple. When something is moving sideways as it falls inward, it cannot collapse straight down. Instead, it curves, circles, and spreads out. A familiar example helps. Imagine slowly pulling a loose thread toward the center of a table while gently nudging it sideways. Instead of piling up neatly, it traces a broad arc, gradually forming a flattened loop around the center. The sideways motion does not stop the inward pull, it redirects it. The same principle applies to gas falling into a galaxy. As hydrogen and helium drift inward under gravity, their slight sideways motions become more pronounced. As the gas contracts, those motions speed up, not because anything adds energy, but because motion becomes concentrated into a smaller region. The result is rotation. Rotation changes everything. Gas that rotates cannot collapse equally in all directions. Motion resists compression along the plane of rotation, while allowing matter to settle more easily above and below that plane. Over time, this imbalance causes the gas to flatten into a broad, thin structure. A disk begins to form. This flattening is not forced. It is the natural outcome of gravity working alongside conserved motion. The gas continues to fall inward, but it does so along curved paths, gradually organizing itself into a rotating disk around the galaxy's center. Importantly, this process does not require precision or symmetry. Even irregular, turbulent gas clouds tend to flatten as rotation becomes dominant. Collisions between gas particles dissipate energy, allowing material to settle into more orderly orbits. Motion becomes smoother. Paths align. Numerical simulations used in modern astrophysics show this behavior repeatedly. When gas is allowed to cool, lose energy, and conserve angular momentum inside a gravitational well, disks emerge without special instructions. They are not imposed by initial conditions. They arise because physics allows no simpler outcome. What emerges is not a rigid structure, but a dynamic one. Gas flows inward through the disk. Stars form within it. Spiral patterns appear as regions of higher density rotate and shear under gravity. These spirals are not permanent objects. They are patterns, constantly forming and dissolving as stars orbit, and gas responds to subtle disturbances. A spiral galaxy is less like a fixed design, and more like a slow-moving current, always changing, always flowing. This distinction matters. Disks are stable without being static. They persist for billions of years, but their details shift continuously. Star formation migrates. Arms wind and unwind. Gas is consumed and replenished. The disk remains recognizable even as its contents evolve. Rotation also explains why disks are relatively thin compared to their width. Motion within the plane supports the structure against collapse, while motion perpendicular to the plane is damped by collisions and energy loss. Over time, the system settles into its flattest, most efficient configuration. Gravity prefers compactness. Motion prefers spread. The disk is the compromise. This compromise produces order without requiring calm. Turbulence still exists. Gas clouds collide. Stars move on slightly tilted orbits. But the overall structure holds, guided by the balance between inward pull and sideways motion. Not all galaxies form disks, and this is important to note. Disk formation depends on conditions: a steady supply of gas, relatively gentle growth, limited disruption. When these conditions are met, disks are the natural result. When they are not, structure takes other forms. This is why disks are common but not universal. Many galaxies show clear rotation and flattened shapes. Others do not. The presence or absence of a disk records a galaxy's history, not a universal rule. Observations support this picture. Spiral galaxies, including the Milky Way, show clear rotational patterns, with stars and gas orbiting in a common direction. The speed of rotation varies with distance from the center, reflecting the combined influence of visible matter and dark matter. In these systems, rotation is not decorative, it is foundational. Without rotation, galaxies would collapse into dense, chaotic systems. With too much disturbance, disks would be torn apart. The fact that disks exist at all tells us that many galaxies experienced long periods of relatively gentle evolution, allowing motion to organize matter rather than scramble it. There is subtle elegance to this outcome. Order does not require stillness. It emerges from motion constrained by simple rules. Gravity pulls inward. Energy is lost through radiation. Motion is conserved. From these ingredients, a disk appears. Spiral galaxies often become the most visually striking outcome of this process, but they are not guaranteed endpoints. Disks can be disrupted by interactions, mergers, or strong internal feedback. They can thicken, warp, or dissolve. Nothing about them is permanent. Yet while they last, they provide stable environments for star formation over immense spans of time. Gas can circulate, cool, and collapse in recurring patterns. Stars can form gradually rather than all at once. Chemical enrichment proceeds steadily. This makes disks especially important for long-lived galaxies. Their order is not imposed from outside. It grows from within, shaped by the quiet persistence of motion that never fully disappears. Even as galaxies evolve, merge and change, the imprint of rotation remains one of the clearest signatures of how they came to be. With disks established, galaxies acquire a recognizable shape. Not final, not fixed, but coherent. And with coherence comes contrast. Because not all galaxies follow this path, and the ones that do not tell a different story entirely. Galaxies do not grow in isolation. As the universe evolves, gravity draws not only gas and stars inward, but entire galaxies toward one another. On the largest scales, matter flows along filaments of the cosmic web, gathering into groups and clusters where encounters become increasingly likely. When galaxies meet, nothing explodes. There are no fiery collisions between stars. The distances between individual stars are so vast that direct impacts are extraordinarily rare. Instead, the interaction unfolds through gravity alone, slowly and relentlessly reshaping everything involved. Two galaxies approaching one another begin to feel each other's gravitational pull long before they touch. Their shapes distort. Tidal forces stretch stars into long arcs and streams. Gas clouds are drawn out of their original orbits, compressed in some regions and dispersed in others. The process is gradual, often taking hundreds of millions or even billions of years from first approach to final settling. During these encounters, stars behave very differently from gas. Stars are essentially collisionless. They pass by one another freely, responding only to the changing gravitational landscape. Their orbits are altered, scrambled, and redistributed, but the stars themselves remain intact. Gas, by contrast, is collisional. As gas clouds from different galaxies interact, they compress, shock, and heat. This can trigger bursts of star formation as dense regions collapse under their own gravity. At the same time, energy injected by feedback processes can heat gas and prevent further collapse, adding complexity to the outcome. What emerges from a major merger is not a larger disk, but something more rounded and less ordered. Elliptical galaxies form when repeated interactions disrupt rotational structure. The ordered motion that supports a disk is fragile. When two rotating systems merge, their angular momenta rarely align. Instead of reinforcing rotation, they cancel it out in different directions. The result is a galaxy where stars move on randomly oriented orbits, tracing elongated paths that fill a roughly spherical or ellipsoidal volume. There is no dominant plane, no coherent rotation to flatten the system. An elliptical galaxy lacks a disk not because it never had one, but because its history erased it. The stars in such galaxies still obey gravity. They still orbit the center, but their motions are distributed in many directions, producing a smooth, rounded appearance rather than a flattened one. Gas fares no better. Much of it is either consumed rapidly in merger-driven star formation, or heated and expelled by feedback from stars and central black holes. What remains is often hot and diffuse, poorly suited to forming new stars. This is why many elliptical galaxies appear red and quiet. Their stars are old, their gas reservoirs are depleted or too hot to collapse efficiently. Star formation slows to a crawl. Observational surveys have made this picture increasingly clear. Large projects such as the Sloan Digital Sky Survey have mapped the positions, shapes and motions of millions of galaxies. When astronomers compare galaxy morphology with environment, a pattern emerges. Dense regions such as clusters are dominated by elliptical and spheroidal galaxies. Isolated regions more often host disks and spirals. Environment leaves a fingerprint. Galaxies that live in crowded neighborhoods experience more interactions. More encounters mean more chances for disks to be disrupted and rotation to be lost. Over time, repeated mergers transform orderly systems into more chaotic ones. This does not mean that elliptical galaxies are featureless or dull. Their smooth appearance hides a rich internal structure. Stellar populations record multiple generations of star formation. Chemical abundances reflect a complex assembly history. Subtle motions reveal the lingering influence of past mergers. Even their sizes tell a story. Some ellipticals grow large not by forming stars internally, but by absorbing smaller galaxies over time. Each merger adds stars without restoring order, puffing up the galaxy and increasing its mass. It is important to avoid misleading language here. These interactions are often described as violent, but the violence is gravitational, not explosive. Stars are not destroyed, planets are not shattered. The drama unfolds through slow changes in motion and structure. If watched in fast forward, the process would look like a slow dance rather than a crash. This distinction matters because it reinforces a central theme of galaxy formation. Change does not require catastrophe. Gravity reshapes systems gently but persistently, given enough time and enough interactions. Elliptical galaxies are not failures of disk formation. They are records. Their shapes encode their past. A smooth, rounded profile suggests repeated mergers and interactions. A lack of rotation points to angular momentum that has been redistributed rather than conserved. A quiet present hints at a more active past. In this way, galaxy morphology becomes a kind of historical document. By observing shape, motion, and environment, astronomers infer the sequence of events that led to the present state. Some galaxies bear scars openly, in the form of tidal streams and distorted outlines. Others appear settled, their tumultuous histories smoothed out over time. Both tell the same story in different ways. Mergers also operate across scales. Small galaxies merge with larger ones. Groups combine into clusters. The universe builds structure hierarchically, assembling big systems from smaller pieces. This expansion of scale is essential. Galaxy formation is not just about how matter behaves inside a single gravitational well. It is about how those wells interact, overlap, and merge across the cosmic landscape. Seen from this perspective, no galaxy is truly alone. Each is part of a larger flow of matter shaped by gravity over billions of years. Some paths lead to graceful disks, others to rounded ellipticals. Neither outcome is preferred. Both are natural consequences of history. What distinguishes them is not destiny, but experience. By the time galaxies are forming stars, building disks, and colliding with neighbours, they are already embedded in a structure far larger than themselves. No galaxy exists in true isolation. Each one grows within a vast pattern that spans the observable universe, a pattern shaped by gravity, acting over billions of years. On the larger scales, matter arranges itself into what astronomers call the cosmic web. This structure is not imposed or designed. It emerges naturally from the same tiny density variations present in the early universe, amplified slowly by gravity and guided by the invisible framework of dark matter. The cosmic web is made up of three dominant features. There are filaments, long thread-like regions of higher density that stretch across tens and sometimes hundreds of millions of light-years. Along these filaments, galaxies are not scattered randomly. They line up, tracing the underlying distribution of mass like frost forming along invisible cracks. There are clusters, dense nodes where multiple filaments intersect. These regions contain hundreds, or even thousands of galaxies bound together by gravity, surrounded by enormous reservoirs of hot gas and dark matter. Clusters are among the most massive gravitationally bound structures in the universe. And then there are voids. Voids are vast regions where matter is scarce. They can span tens of millions of light-years, containing few galaxies and little gas. These regions are not empty, but compared to filaments and clusters, they are profoundly underdense. Gravity has slowly drained material away from them, feeding the surrounding structures. Together, filaments, clusters, and voids form a connected network that fills space. This pattern did not appear suddenly. It developed gradually as dark matter collapsed under its own gravity, forming sheets and threads that intersected and thickened over time. Ordinary matter followed these patterns, falling into the same gravitational wells and lighting them up with stars. In this sense, galaxies are tracers. They do not define the cosmic web, they reveal it. When astronomers map the positions of millions of galaxies, the web becomes visible. Dense strands of galaxies outline filaments. Crowded regions mark clusters. Large gaps highlight voids. The light traces the mass, even though most of that mass remains invisible. This connection between galaxies and dark matter distribution has been tested extensively through observation and simulation. Large cosmological simulations, run by international collaborations using some of the most powerful computers available, begin with conditions measured from the early universe. They evolve matter forward in time using gravity, gas physics, and expansion alone. When dark matter is included, a web-like structure emerges reliably. When it is not, the structure fails to form. These simulations show filaments growing naturally, drawing matter inward along preferred directions. Gas flows along these filaments toward clusters, feeding galaxies as they grow. Star formation is not evenly distributed across space. It is enhanced in dense environments and suppressed in emptier ones. Galaxies grow where the web delivers material. This environmental influence has profound consequences. A galaxy located deep within a filament experiences a very different history from one drifting near the center of a void. Gas supply, interaction rates, and merger frequency all depend on position within the web. In dense regions, galaxies encounter one another more often. They are more likely to merge, lose gas, or have star formation disrupted by their surroundings. In clusters, hot intracluster gas can strip material from galaxies as they move through it, further suppressing star formation. In quieter regions, galaxies can grow more gently. Gas accretion proceeds slowly and steadily. Disks are more likely to survive. Star formation can continue over longer periods without major interruption. The cosmic web therefore acts as a kind of large-scale regulator. It does not dictate the fate of individual galaxies, but it sets the conditions under which their internal processes unfold. Gravity still governs collapse. Feedback still regulates star formation, but environment determines how often those processes are disturbed or reinforced. This explains why galaxy properties correlate so strongly with location. Surveys show that elliptical galaxies are more common in dense environments, while spiral galaxies dominate less crowded regions. Star formation rates decline toward cluster centers. Gas-rich systems are more prevalent along filaments feeding into clusters. These patterns are not coincidences. They reflect billions of years of interaction between galaxies and their surroundings. Importantly, the cosmic web is not static. Filaments continue to draw matter inward. Clusters grow by absorbing galaxies and smaller groups. Voids expand as matter drains away. The web evolves slowly, but continuously, reshaping the environment in which galaxies live. Galaxies respond to these changes. A galaxy that begins life in a filament may eventually fall into a cluster, experiencing a dramatic shift in conditions. Gas supply may be cut off, interactions may increase, star formation may decline. The galaxy's internal evolution cannot be separated from its journey through the web. Even the chemical makeup of galaxies is influenced by environment. Regions with frequent star formation enrich gas more rapidly. Mergers redistribute heavy elements. Outflows driven by stars and black holes can pollute surrounding space, spreading metals along filaments and into intergalactic gas. In this way, the cosmic web helps shape chemical evolution across vast distances. Heavy elements forged in stars do not remain confined to single galaxies. They are carried outward by winds, stripped during interactions, and mixed into the larger environment. Later generations of galaxies form from this enriched material, inheriting a chemical history shaped by their surroundings. The web becomes not just a scaffold for matter, but a medium through which material, energy, and history circulate. One of the most striking aspects of the cosmic web is how inevitable it appears. Given the initial conditions measured in the early universe and the known laws of physics, simulations repeatedly produce similar large-scale patterns. Change the details slightly, and the web still forms. The precise arrangement varies, but the overall structure persists. This robustness suggests that the cosmic web is not a fragile outcome, but a natural consequence of gravity acting on expanding matter. There is a quiet elegance in this result. From near uniform beginnings, the universe develops a richly textured structure without guidance or intention. Small differences grow, matter flows, space stretches. Over time, complexity emerges. Galaxies are not isolated achievements, they are local expressions of a global pattern. Seen from this perspective, galaxy formation cannot be fully understood by studying galaxies alone. Their shapes, star formation histories, and chemical compositions are influenced by where they sit within the web, how material reaches them, and how often their paths cross those of others. The cosmic web provides context. It explains why some galaxies grow large while others remain small, why some burn brightly and fade early, while others glow gently for billions of years, why structure on the scale of stars is linked to structure on the scale of hundreds of millions of light years. Everything is connected, not mysteriously but mechanically. Gravity ties the universe together across scales. Dark matter lays down the framework. Ordinary matter follows. Light reveals what mass has already decided. With galaxies now placed firmly within this larger environment, their evolution becomes inseparable from the flow of matter around them. The next step is to understand how this environment influences what galaxies are made of, not just how they are arranged. Because growth is not only about where galaxies live, but about what they become. As galaxies continue to form stars over long stretches of time, they begin to change in a way that is subtle but irreversible. Not in shape or size alone, but in composition. With each generation of stars, galaxies slowly rewrite their own chemical makeup. In the earlier stages, galaxies are chemically simple. Their gas consists almost entirely of hydrogen and helium, the elements forged in the first few minutes after the Big Bang. Everything heavier must be created later, inside stars themselves. This means that star formation is not just a way of producing light, it is a way of producing matter. Every time a star forms, lives and dies, it alters the material around it. Light elements are fused into heavier ones in stellar cores. Those elements are then released back into the surrounding gas through stellar winds or supernova explosions. The next generation of stars forms from this altered mixture, inheriting the chemical history of what came before. Over time, galaxies grow older not simply by accumulating stars, but by becoming chemically richer. Astronomers describe this process using the term metallicity. In astronomy, metals mean any element heavier than helium. A galaxy with low metallicity contains very little of these heavier elements. A galaxy with high metallicity has been enriched by many cycles of star formation. The increase in metallicity is gradual. No single star dramatically changes a galaxy's composition. But across millions or billions of stars, the effect becomes unmistakable. Carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements accumulate in the interstellar gas. This chemical evolution transforms how galaxies behave. Heavier elements are extremely effective at cooling gas. Their complex atomic structures allow them to emit energy efficiently through radiation. As metallicity increases, gas can lose heat more easily, making it simpler for clouds to collapse and form new stars. In this way, chemical enrichment feeds back into star formation itself. Early galaxies, poor in heavy elements, form stars differently from later galaxies that are metal-rich. The balance between heating and cooling shifts. Fragmentation becomes more efficient. Star formation moves towards smaller, longer-lived stars. The universe becomes better at making stars precisely because it has already made stars. Understanding this gradual enrichment required a way to measure composition across enormous distances. That tool is spectroscopy. Spectroscopy works by breaking light into its component colors, revealing patterns that act like fingerprints for different elements. Each element absorbs and emits light at specific wavelengths. By examining these patterns in starlight or glowing gas, astronomers can identify which elements are present and in what relative amounts. This technique does not require collecting samples. It works across vast stretches of space. Light that has travelled millions or billions of years carries within it a record of the matter that produced it. Spectroscopy became a cornerstone of astrophysics in the late 19th and early 20th centuries, and was refined throughout the 20th century as instruments improved. It allowed astronomers to move beyond simply locating stars and galaxies, and begin analysing what they are made of. With spectroscopy, galaxies are no longer just shapes on the sky. They become chemical systems. Measurements show clear trends. Younger galaxies, observed as they were early in cosmic history, tend to have lower metallicity. Older galaxies, especially massive ones, are more chemically enriched. Within a single galaxy, metallicity often varies with location, typically higher in central regions where star formation has been most intense. These gradients tell stories. A high central metallicity suggests prolonged star formation and effective recycling of material. Lower metallicity in outer regions suggests slower growth or accretion of more pristine gas from the surrounding environment. Galaxies do not enrich evenly. Their internal histories are layered. Stellar evolution theory, developed and refined across the 20th century, explains why stars enrich their surroundings in predictable ways. The mass of a star determines its lifetime and its contribution to chemical evolution. Massive stars burn quickly and explode as supernovae, producing large quantities of heavy elements in a short time. Smaller stars burn slowly, contributing less dramatic but longer-lasting enrichment through gentle outflows. Different elements trace different timescales. Elements like oxygen and magnesium are produced primarily by massive stars and appear early. Elements like iron accumulate more gradually, as they are produced in events involving longer-lived stars. By comparing the relative abundances of different elements, astronomers reconstruct the pace and timing of star formation in a galaxy. This makes chemical composition a kind of clock, not a precise one, but a reliable one. It reveals whether a galaxy formed most of its stars quickly or slowly, whether it experienced bursts of activity or steady growth, whether it has been enriched primarily by early generations or by prolonged star formation. Chemical evolution also connects galaxies to their environments. Gas flowing into a galaxy from the cosmic web often has lower metallicity than gas already inside. When this gas mixes in, it can dilute the overall composition, temporarily lowering metallicity and altering star formation behavior. Outflows work in the opposite direction. When feedback pushes enriched gas out of galaxies, heavy elements spread into surrounding space. Over time, this process enriches the intergalactic medium itself, ensuring that later forming galaxies are born into a chemically altered universe. No galaxy evolves alone, chemically or otherwise. Even within galaxies, chemical evolution is not smooth. Star formation proceeds in clusters and regions. Supernovae enrich some areas more than others. Mixing takes time. The result is a patchwork of chemical conditions that gradually even out over long periods. This unevenness matters because stars forming in different environments inherit different properties. Metallicity influences stellar temperature, brightness, and lifetime. It affects how easily planets can form later on. It shapes the kinds of systems a galaxy can support. As galaxies age, their stellar populations shift. Early generations dominated by massive, short-lived stars give way to populations rich in smaller, longer-lived ones. The overall colour of a galaxy changes. Blue, star-forming systems gradually become redder and quieter as gas supplies diminish and star formation slows. These changes are not sudden, they unfold over billions of years. From a distance, a galaxy may look stable. From a chemical perspective, it is anything but. Every generation of stars leaves an imprint. Every episode of star formation alters the raw material for the next. This ongoing transformation is one of the clearest signs that galaxies are not static objects. They are processes. Their present state reflects everything that has happened within them and around them since their formation. Chemical enrichment ties together many of the themes already encountered. Gravity gathers matter, cooling allows collapse, stars ignite, feedback regulates growth, and chemistry records it all. The universe does not reset between generations, it remembers. As instruments improve, astronomers can now measure chemical composition in galaxies across vast spans of time. By observing distant galaxies, they look back to earlier stages, comparing young systems with mature ones. Differences in metallicity, star formation rate, and structure reveal how galaxies change as the universe ages. This ability to observe galaxies at different points in their chemical lives opens a new window, not just into how galaxies form, but into how they mature. With that perspective in place, attention can shift from evolution within galaxies to the act of observing that evolution across cosmic time itself. By the time galaxies begin to grow chemically richer and structurally more complex, a natural question follows. How is any of this known at all? How can events that unfolded billions of years ago be studied with confidence from a small planet orbiting an ordinary star? The answer lies not in travelling through time, but in understanding how light travels through space. Light does not arrive instantly. It moves at a finite speed, crossing vast distances year by year. When light leaves a distant galaxy, it carries information about that galaxy at the moment it was emitted. By the time that light reaches Earth, the galaxy itself may have changed dramatically. In this way, looking outward is also looking backward. This idea is known as look-back time. A galaxy 1 million light-years away is seen as it was 1 million years ago. A galaxy 1 billion light-years away is seen as it was 1 billion years ago. The farther away an object lies, the earlier the moment being observed. The universe becomes a layered archive, with distance corresponding to age. On cosmic scales, this effect is profound. The most distant galaxies observable today are seen as they existed when the universe was only a small fraction of its current age. They appear younger, smaller, more chaotic, and often very different from galaxies nearby. This is not because early galaxies were poorly behaved, it is because they were still forming. As light travels through expanding space, something else happens. The space between galaxies stretches while the light is in transit, lengthening the light's wavelength. Shorter wavelengths shift toward longer ones. Blue light becomes redder. Ultraviolet light slides into the visible or infrared. This stretching is known as redshift. Redshift is not caused by galaxies simply moving away through space, like cars driving apart. It reflects the expansion of space itself. As space stretches, so does the light moving through it. The greater the distance, the greater the stretching, and the higher the redshift. By measuring redshift, astronomers estimate how far away a galaxy is and how long its light has been travelling. Redshift becomes a kind of timestamp, linking observation directly to cosmic history. What makes this powerful is that redshift does not require speculation. It is measured directly from the spectrum of light. Known atomic patterns appear shifted toward longer wavelengths by predictable amounts. From this shift, distance and look-back time can be inferred reliably. Using this method, astronomers build a timeline of galaxy evolution. Nearby galaxies show mature structures, ordered disks, older stellar populations, higher metallicities. More distant galaxies seen earlier in time appear clumpier, more gas-rich, and less settled. Their stars form rapidly. Their shapes are irregular. Their chemical composition is simpler. This sequence is not inferred from theory alone, it is observed. For much of the 20th century, studying very distant galaxies was limited by technology. Light from the earliest galaxies is faint and heavily redshifted, often pushed into the infrared. Ground-based telescopes struggle to detect it clearly through Earth's atmosphere. This limitation shaped expectations. Early models predicted that the first galaxies would be small, dim, and difficult to detect. Observations hinted at this picture, but data remained sparse. That situation changed with the launch of the James Webb Space Telescope. Designed specifically to observe infrared light, this telescope allows astronomers to study galaxies whose light has been stretched far beyond the visible range. For the first time, it became possible to observe galaxies as they existed only a few 100 million years after the Big Bang. What emerged was both reassuring and surprising. Many early galaxies appeared brighter and more massive than expected. Some showed signs of surprisingly rapid star formation. Others displayed structured shapes earlier than models had predicted. The universe, it seemed, had been efficient at building galaxies quickly, even under primitive conditions. At the same time, the broad trends remained intact. Early galaxies were chemically simple, their structures were less settled, their star formation rates were often intense but short-lived. As time progressed, galaxies grew larger, calmer, and more diverse. These observations did not overturn existing theory. They refined it. They demonstrated that galaxy formation is not a slow uniform process, but a flexible one. Under the right conditions, galaxies can assemble rapidly. Under others, they grow gradually. The laws remain the same, the outcomes vary. Crucially, this progress required patience. Observing the distant universe is not like taking a snapshot. It involves collecting faint light over long periods, carefully separating signal from noise, and comparing results across many observations. Individual images rarely tell the full story. Patterns emerge only through accumulation. Large surveys map thousands or millions of galaxies at different distances. Spectroscopic studies measure redshift and composition. Deep field observations stare at seemingly empty patches of sky for weeks, revealing countless faint objects hidden from casual view. This slow approach mirrors the subject itself. Galaxy formation unfolds over billions of years. Understanding it requires restraint and persistence rather than speed. There is also an important limitation built into this method. No observation shows the universe as it is everywhere at once. Each distance reveals a different time. Astronomers reconstruct history by comparing populations, not by watching individual galaxies age. This requires care. Galaxies observed at different distances are not ancestors and descendants in a direct sense. They are representatives of different eras. Drawing conclusions involves statistical reasoning, careful modeling, and repeated cross-checking between theory and observation. Despite these challenges, the consistency is striking. Independent measurements using different instruments, wavelengths, and methods converge on the same broad picture. The universe began simple. Structure emerged. Galaxies grew, interacted, enriched themselves, and diversified. Redshift and look-back time provide the thread that connects these observations into a coherent narrative. They also introduce humility. No telescope can see beyond the observable universe. No observation captures the earliest moments directly. Light from the first stars and galaxies is faint, stretched, and sometimes lost beyond detection. Even the most powerful instruments operate near the edge of what is possible. This is not a failure of science. It is a boundary condition. Understanding improves as tools improve, but limits remain. Observations always reflect a combination of what exists and what can be measured. What matters is that theory and observation meet. Predictions about early galaxy formation are tested against data. When discrepancies appear, models are adjusted. When agreement strengthens, confidence grows. The process is iterative, cautious, and grounded in evidence. Looking back through time is therefore not an act of imagination. It is a methodical reconstruction based on light, motion, and physics. Every distant galaxy observed is a data point from an earlier chapter of cosmic history. Together, they form a timeline that stretches from the present day back toward the universe's beginnings. As observations push deeper, they also reveal where understanding remains incomplete. Some early galaxies appear unexpectedly massive. Some form stars faster than models anticipate. Some environments behave in ways not yet fully explained. These are not contradictions. They are invitations. They signal where assumptions need refining, where additional physics may play a role, or where early conditions differed from expectations. Observation does not close the story. It guides it. By anchoring theory to what is actually seen, astronomy maintains its balance. Ideas remain grounded. Speculation remains constrained. With the universe now observed across time as well as space, the focus naturally turns to the places where observation and explanation still diverge. The edges where understanding thins, not because evidence is lacking, but because nature remains subtle. That is where the next questions begin. By this point, a broad picture of galaxy formation has emerged that is remarkably consistent. Gravity gathers matter. Dark matter shapes structure. Gas cools. Stars ignite. Feedback regulates growth. And galaxies evolve within a cosmic web. Yet consistency does not mean completeness. When astronomers compare detailed observations with the most advanced simulations, small but persistent mismatches remain. These gaps are not signs that the framework is wrong. They are signs that the story is still being filled in. Modern models of galaxy formation are built using computational cosmology. In these simulations, vast volumes of the universe are recreated inside computers, starting from conditions measured in the early universe. Gravity is calculated for trillions of particles. Gas dynamics, cooling, star formation, and feedback are included using well-tested physical laws, translated into algorithms that computers can handle. The results are impressive. Large-scale structure emerges naturally. Filaments form, clusters grow, galaxies appear in roughly the right numbers, sizes, and locations. Many observed trends are reproduced with striking accuracy, and yet, when astronomers look closely, some details do not line up perfectly. One of the most discussed discrepancies involves the earliest galaxies. Observations show that some young galaxies appear brighter, more massive, or more evolved than simulations predict at very early times. According to some models, there should not have been enough time for such large systems to assemble and form stars so efficiently. Yet there they are, visible in deep observations. This does not mean the observations are wrong. Independent instruments and surveys confirm these findings. It also does not mean the simulations are fundamentally broken. Instead, it suggests that certain processes may be more efficient, or may begin earlier than originally assumed. Small changes can matter. Star formation efficiency, the timing of gas cooling, the impact of early feedback, and the behavior of dark matter on small scales all influence outcomes. Adjusting any one of these slightly can shift predictions significantly. The challenge lies in identifying which adjustments reflect reality. Another area of tension concerns galaxy size. Some early galaxies appear compact but extremely bright, while others are surprisingly extended. Simulations can produce both kinds, but not always in the observed proportions. The balance between rapid star formation and structural growth remains an active area of investigation. These discrepancies are not failures, they are diagnostic tools. They tell researchers where assumptions may be incomplete, or where physical processes need more careful treatment. In computational cosmology, models are not static. They are updated continuously as new data arrive. This process mirrors how science has always progressed. Theories are proposed, tested, adjusted, and refined. No model is expected to capture every detail on the first attempt, especially when dealing with systems as complex as galaxies. Feedback is a particularly challenging ingredient. While the broad effects of stellar winds, supernovae, and black hole activity are well established, the exact ways energy couples to gas on small scales are difficult to model precisely. Simulations must approximate processes that occur over distances far smaller than the resolution of the model. Different approaches produce slightly different outcomes. Some generate galaxies that form stars too quickly. Others suppress star formation too strongly. Finding the balance that matches reality across all environments remains an ongoing effort. Dark matter itself introduces uncertainty. Although its gravitational behavior is well constrained, its microscopic nature remains unknown. Most simulations assume a specific type of dark matter that interacts only through gravity. If dark matter behaves differently on small scales, even subtly, this could influence early structure formation. Observations have not yet ruled out all possibilities. Chemical evolution also presents challenges. Simulations track the production and distribution of heavy elements, but mixing processes in real galaxies are complex. Gas flows, turbulence, and feedback redistribute elements unevenly. Matching observed metallicity patterns across different galaxy types is an active area of research. Despite these issues, it is important to note what does work. Simulations successfully reproduce the large-scale distribution of galaxies, the overall history of star formation in the universe, and the broad relationship between galaxy mass, environment, and structure. These successes suggest that the foundational framework is sound. The remaining discrepancies are refinements, not revolutions. Research groups around the world continue to improve these models, incorporating better physics, higher resolution, and more realistic treatments of gas and feedback. International collaborations share data, compare results, and test predictions against new observations. The goal is not to force agreement, but to let evidence guide improvement. There is also an important philosophical point here. Models are tools, not mirrors. They are simplified representations of reality, designed to capture essential behavior without reproducing every detail. Expecting perfect agreement would be unrealistic. What matters is whether models explain patterns, trends, and underlying mechanisms. In this respect, galaxy formation theory has matured significantly. Where earlier generations debated whether galaxies could form at all under known physics, modern research focuses on how efficiently and under what conditions they form. This shift reflects confidence. Uncertainty is now local rather than global. Questions revolve around timing, efficiency, and variation, not basic plausibility. The universe is no longer mysterious in its ability to build structure. It is nuanced. Even disagreement plays a productive role. When simulations and observations diverge, new ideas are tested. Alternative assumptions are explored. Observational strategies are refined. Progress accelerates. There's a gentle humility in this process. Astronomy deals with systems far beyond direct experimentation. No galaxy can be isolated and tested repeatedly. Understanding emerges from comparison, inference, and patience. Models improve not through certainty, but through restraint. As observational tools become more powerful, the pressure on models increases. New data reveal finer detail, exposing both strengths and weaknesses. This is not a crisis. It is how science sharpens itself. Importantly, no single observation overturns the framework of galaxy formation. Instead, many small measurements accumulate, nudging understanding in subtle directions. Adjustments are incremental, not dramatic. This gradual refinement mirrors the universe itself. Just as galaxies grow through slow accumulation rather than sudden creation, understanding grows through steady correction rather than sudden insight. Each mismatch resolved brings theory closer to reality, without ever claiming finality. With this honesty in place, the focus can narrow. Having traced the general processes that shape galaxies across the universe, attention can now turn inward, to a specific system, one whose structure, chemistry, and history can be studied in extraordinary detail, a galaxy whose formation story is not inferred from faint light across billions of years, but reconstructed from stars close enough to measure individually. The Milky Way becomes the next lens through which galaxy formation is examined, not as an exception, but as a detailed case study within the broader cosmic pattern. For all the vast scales involved in galaxy formation, there is one system where the process can be studied in exceptional detail. A galaxy close enough that individual stars can be examined one by one, old enough to preserve traces of its earliest history. Familiar in name, but far from simple in origin. The Milky Way. Far from forming in a single event, the Milky Way assembled gradually over billions of years through a combination of steady gas accretion and repeated mergers with smaller galaxies. Its present form is the outcome of countless quiet interactions rather than any dramatic beginning. The earlier stages of the Milky Way resemble those of other young galaxies. A dark matter halo formed first, gathering gas from the surrounding environment. Hydrogen and helium settled inward, cooled, and began forming stars. At this point, the galaxy was smaller, more chaotic, and far less structured than it is today. As time passed, growth continued along two main paths. The first was gas accretion. The Milky Way drew in fresh material from its surroundings, much of it flowing along filaments of the cosmic web. This gas replenished star-forming regions, allowing new generations of stars to form long after earlier ones had exhausted their fuel. Even today, the Milky Way continues to accrete small amounts of gas, sustaining ongoing star formation. The second path was merger-driven growth. Rather than remaining isolated, the Milky Way absorbed numerous smaller galaxies over its lifetime. These mergers were not catastrophic collisions. They were slow, gravitational encounters in which smaller systems were stretched, disrupted, and gradually incorporated into the larger galaxy. The stars from these absorbed galaxies did not vanish. They became part of the Milky Way's stellar halo, thick disk, and outer regions, carrying with them chemical and dynamical signatures of their origins. This layered assembly is why the Milky Way contains multiple distinct stellar components. There is a thin disk, rich in gas and actively forming stars, rotating in an orderly fashion. There is a thicker disk of older stars with more varied orbits. There is a central bulge containing densely packed stars with complex motions. And surrounding it all is a diffuse halo populated by ancient stars moving on elongated, often tilted paths. Each component reflects a different chapter of the galaxy's history. Understanding this history relies on a field known as galactic archaeology. Much like archaeologists reconstruct human history from layers of soil and artifacts, astronomers reconstruct galactic history from the properties of stars. Age, chemical composition, and motion all act as clues. A star's chemical makeup reveals the environment in which it formed. Its orbit reveals how it has been influenced by the galaxy's gravitational evolution. Its age places it within a timeline stretching back billions of years. By studying large numbers of stars, patterns emerge. Some stars share common motions and compositions, indicating they formed together or arrived together through a merger. Others trace smooth gradients, reflecting long-term internal evolution. Streams of stars moving coherently through the halo betray the remains of smaller galaxies that were torn apart and absorbed. This detailed reconstruction became possible on an unprecedented scale with data from the Gaia mission. By measuring the positions, distances, and motions of more than 1 billion stars, Gaia transformed the Milky Way from a vague spiral into a precisely mapped system. With this information, astronomers can trace stellar orbits backward and forward, identifying groups of stars that share common origins. They can distinguish stars formed inside the Milky Way from those that arrived later. They can estimate when major merger events occurred and how strongly they reshaped the galaxy. One particularly important finding is that the Milky Way experienced significant mergers early in its history, followed by a long period of relatively calm growth. This pattern allowed the disk to form and survive. Repeated major mergers would have destroyed orderly rotation, but the Milky Way appears to have avoided such disruption after its early stages. This quiet middle age is not accidental. It reflects the galaxy's environment and mass, large enough to retain gas and form stars steadily, but not so central within a dense cluster that interactions became unavoidable. The result is a galaxy that has grown steadily rather than explosively. Chemical evidence supports this picture. The metallicity of stars in different regions reveals how star formation progressed over time. Older stars tend to have lower metallicity, reflecting formation from less enriched gas. Younger stars contain higher proportions of heavy elements, produced by earlier generations. Within the disk, metallicity varies with distance from the center, indicating that star formation was more intense in some regions than others. In the halo, stars often show distinct chemical patterns consistent with origins in smaller, less evolved galaxies. These details confirm that the Milky Way is not monolithic. It is a composite system, built piece by piece. What makes this especially striking is how ordinary the Milky Way appears in the broader context of galaxy formation. Its mass, structure, and star formation rate are typical for a spiral galaxy of its kind. There is nothing extreme about it, and yet from within its complexity is extraordinary. Billions of stars, each following its own orbit, gas clouds forming and dispersing, supernovae enriching the interstellar medium, subtle waves and ripples moving through the disk, all of it unfolding according to the same physical principles seen across the universe. The Milky Way is not finished. Star formation continues, though at a slower pace than in its youth. Gas is still accreted. Small satellite galaxies are still being drawn in. The stellar halo continues to grow incrementally. Even now the galaxy is changing. This ongoing evolution reinforces a central theme. Galaxy formation is not something that happened once and ended. It is a continuous process, shaped by environment, history, and chance, but governed by stable physical laws. By studying the Milky Way in detail, astronomers test broader theories of galaxy formation. If models can reproduce its structure, chemistry, and history, confidence grows that those models apply elsewhere as well. If discrepancies appear, they point to refinements needed on larger scales. In this way, the Milky Way serves as both example and laboratory. Its stars act as witnesses to events long past. Its structure records billions of years of gradual change. Its present state reflects an accumulation of small influences rather than singular drama. There is a quiet reassurance in this story. Even in a universe shaped by immense forces and vast scales, complexity does not require chaos. Order can emerge through patience. Structure can survive through moderation. The Milky Way stands as evidence that galaxy formation is not a fleeting event, but a long conversation between gravity, matter, and time. And that conversation is still ongoing. It is tempting to think of galaxies as finished objects, vast ancient systems that assembled long ago and have been slowly fading ever since. The evidence does not support that picture. Galaxies are still forming, not everywhere and not all at once, but continuously, unevenly, and often quietly. Even in the present-day universe, new stars ignite, gas flows inward, and small systems take shape under the same physical laws that govern the earliest galaxies. One of the clearest reminders of this continuity comes from dwarf galaxies. Dwarf galaxies are small, faint systems containing far fewer stars than large spirals like the Milky Way. Some host only a few million stars, compared to the hundreds of billions found in larger galaxies. Despite their modest size, dwarfs are among the most numerous galaxies in the universe. They're also among the most revealing. Many dwarf galaxies are still actively forming stars today. Their gas reservoirs have not been exhausted. Their internal processes continue at a pace more reminiscent of the early universe than of mature systems. In some cases, star formation occurs in bursts, separated by long, quiet intervals. In others, it proceeds slowly but steadily. Nearby examples make this easy to see. The Large Magellanic Cloud, a companion of the Milky Way, contains large star-forming regions where massive young stars illuminate surrounding gas. These regions are not relics. They are current, ongoing sites of stellar birth. Dwarf galaxies matter not because they are small, but because they show that galaxy formation did not stop once the largest systems assembled. The same processes continue wherever conditions allow. Another key ingredient in ongoing galaxy growth is gas. Stars consume gas. Supernovae and stellar winds redistribute it. Over time, one might expect galaxies to run out of raw material entirely. Yet many galaxies continue forming stars long after their original gas should have been depleted. The reason is replenishment. Galaxies are not closed systems. They interact constantly with their surroundings, drawing in fresh material from intergalactic space. One of the most important mechanisms for this is cold gas accretion. Cold gas accretion refers to the slow inflow of relatively cool hydrogen gas from the cosmic web into galaxies. Rather than being shock-heated to extreme temperatures before settling, this gas can stream along filaments and enter galactic halos without becoming fully ionized. Once inside, it cools further, settles into disks and becomes available for star formation. This process is difficult to observe directly, because the gas is diffuse and faint. Much of what is known comes from indirect evidence, and from simulations that match observed star formation rates. When accretion is included, galaxies can sustain star formation over billions of years. Without it, they fade too quickly. Cold gas accretion helps explain why galaxies like the Milky Way are still forming stars today. Although the rate is lower than in the past, it has not dropped to zero. New stars continue to appear, quietly extending the galaxy's stellar population. Continuity also appears in the broader population of galaxies. Across the universe, there is no sharp dividing line between young and old systems. Instead, galaxies occupy a wide range of states. Some are actively forming stars, others are mostly dormant. Many fall somewhere in between, with low but persistent activity. Even massive galaxies that appear quiet often show signs of residual star formation in their outskirts or central regions. Gas may trickle in slowly. Small companions may be absorbed. Nothing truly stands still. This ongoing growth is most obvious when galaxies are observed across different environments. In dense clusters, star formation is often suppressed, but even there, smaller systems can continue forming stars. In less crowded regions, galaxies retain gas more easily and evolve more gently. Environment shapes pace, not possibility. Dwarf galaxies are especially sensitive to these conditions. A dwarf drifting alone in a low-density region may retain gas for billions of years, forming stars sporadically. A similar dwarf passing near a larger galaxy may lose its gas through tidal forces or heating, shutting down star formation entirely. This diversity reinforces a central point. Galaxy formation does not follow a universal schedule. It depends on mass, environment, and history. The universe does not flip a switch and move on. There is also a longer perspective to consider. In cosmic terms, the present day is not the end of galaxy formation. The universe is still relatively young compared to its potential lifespan. Dark matter halos continue to merge. Gas continues to flow. New structures continue to appear on small scales. Even as the overall star formation rate in the universe declines, local pockets of activity persist. The universe is not winding down uniformly. It is changing character. One reason this matters is that dwarf galaxies may resemble the earliest galaxies in important ways. Their low metallicity, simple structure, and intermittent star formation echo conditions thought to prevail in the early universe. By studying dwarfs nearby, astronomers gain insight into processes that were common billions of years ago. This makes nearby systems laboratories for understanding the past. At the same time, ongoing star formation reminds us that galaxy evolution is not only about history, it is about continuity. The same physical principles apply now as they did when the first galaxies formed. Gravity still gathers matter, gas still cools, stars still ignite. The universe has not changed the rules, only the conditions. There is quiet comfort in this idea. Complexity does not require urgency. Growth does not demand completion. Galaxies can evolve slowly, adapting to circumstances without ever reaching a final state. Even humour has room here. If galaxies had a motto, it might be something like, "Still in progress." This perspective shifts how galaxy formation is understood. Rather than a finished chapter in cosmic history, it becomes an ongoing process, one that extends from the earliest times to the present and beyond. Dwarf galaxies, cold gas accretion, and persistent star formation all point to the same conclusion. The universe did not build galaxies and move on. It continues to build them, quietly and selectively, wherever conditions allow. Recognizing this removes the temptation to look for endpoints. Galaxies are not monuments, they are systems. They grow, adjust, slow down, and sometimes reawaken. Their present state reflects a balance between past accumulation and ongoing change. Nothing about them is final. This continuity prepares the ground for a deeper question. If galaxies are still forming, still changing, still responding to their environments, then their significance lies not just in how they came to be, but in what they make possible. Understanding that significance requires stepping back from mechanics and considering why galaxies matter at all. At first glance, galaxies can seem like scenery. Vast collections of stars arranged into spirals, ellipses, or irregular clouds, impressive in scale but distant from everyday relevance. Yet when examined more closely, galaxies turn out to be more than containers of stars. They are long-term environments, shaping what kinds of structures can exist and how long they can persist. In a universe governed by gravity and expansion, stability is not guaranteed. Left on its own, matter can disperse, gas can thin out, energy can randomize motion. Galaxies counteract this tendency by providing gravitational anchoring over immense spans of time. Their combined mass, dominated by dark matter, creates regions where material can remain bound for billions of years. This matters because many processes require patience. Stars do not form instantly. Planetary systems take millions of years to assemble. Chemical enrichment unfolds over multiple generations of stars. None of this is possible in environments that are short-lived or violently unstable. Galaxies provide the continuity required for slow processes to unfold. In this sense, galaxies act as stabilizing frameworks. Their gravitational potential wells keep gas from drifting away too quickly. Their rotation and structure distribute material in predictable ways. Even when star formation fluctuates, the overall system remains intact long enough for complex outcomes to emerge. The importance of this stability becomes clearer when comparing galaxies to regions without it. In intergalactic space, matter is sparse and diffuse. Star formation is essentially impossible. Even within galaxies, regions that lose gas or experience strong heating often stop forming stars entirely. Structure enables persistence. Galaxies also regulate extremes. Their size and mass buffer internal systems from dramatic external influences. Supernova explosions, stellar winds, and even black hole activity release enormous energy locally. But galaxies absorb and redistribute that energy rather than being torn apart by it. This buffering allows star formation to proceed in a measured way rather than burning itself out immediately. Another key role galaxies play is in chemical preparation. As discussed earlier, galaxies accumulate heavy elements over time. These elements are not distributed randomly. They are mixed into gas clouds, incorporated into stars, and eventually recycled. Later generations of stars form from material that has been chemically processed many times. This enrichment has consequences. Heavier elements influence how stars behave, how long they live, and how they interact with surrounding matter. They also enable the formation of solid particles, dust grains, and eventually rocky bodies. Without this chemical groundwork, later structures simply cannot form. Galaxies therefore act as chemical reservoirs, steadily increasing the complexity of the material within them. Planet formation is an indirect but important consequence of this process. Observations show that stars forming in metal-rich environments are more likely to host planets, particularly rocky ones. This does not mean planets are rare in low metallicity regions, but it does suggest that certain kinds of planetary systems become more common as chemical enrichment proceeds. The connection here is empirical, not speculative. Astronomers observe planets around stars in the Milky Way and in nearby galaxies. They measure how planet occurrence varies with stellar composition. These measurements indicate that galaxies which have undergone extended periods of star formation are more likely to host stars with diverse planetary systems. This does not imply intent or purpose. It reflects physical requirements. Solid materials are needed to build solid bodies. Those materials come from stellar processes. Galaxies that persist long enough to produce and recycle heavy elements create conditions where such structures are more likely to arise. Astrobiology frameworks build on this logic. Rather than asking whether life exists elsewhere, astrobiology examines the conditions under which complex chemistry can occur. It studies energy sources, chemical availability, and environmental stability. Within this framework, galaxies are not guarantees of anything. They are enabling environments. They provide long-term access to energy through stars. They provide chemical diversity through stellar evolution. They provide stability through gravitational structure. This combination does not ensure outcomes, but it makes certain outcomes physically possible. It is also important to avoid exaggeration. Not all galaxies are equally accommodating. Some are too small to retain gas for long. Others experience frequent disruptions that limit long-term stability. Some environments are harsh, with intense radiation or rapid gas loss. Galaxies vary widely. What matters is that galaxy formation produces a range of environments, some of which are conducive to slow, cumulative processes. The universe does not optimize for any particular outcome. It explores possibilities. Even within a single galaxy, conditions differ dramatically. Dense central regions behave differently from quiet outer disks. Star formation rates vary. Chemical composition changes with location. Stability is relative, not absolute. Yet despite this variation, galaxies endure. A typical large galaxy exists for billions of years. Over that time, countless processes unfold. Stars are born and die. Gas cycles through different phases. Structure evolves gradually. The system remains recognizable even as its contents change. This persistence is rare on cosmic scales. On the larger scales, expansion dominates. On the smaller scales, interactions are fleeting. Galaxies occupy a middle ground where gravity, motion, and time find a workable balance. This balance also explains why galaxies matter scientifically. They are natural laboratories where many physical processes interact. Gravity, thermodynamics, nuclear physics, radiation, and chemistry all operate together within a single system. Studying galaxies allows these interactions to be observed in context rather than isolation. Galaxies also link different scales of the universe. What happens inside stars influences galaxy evolution. What happens in galaxies influences the chemical state of intergalactic space. What happens on cosmic scales influences how galaxies grow. The boundaries are porous. Understanding galaxies therefore improves understanding elsewhere. At the same time, restraint is essential. It is tempting to frame galaxies as special or purposeful. The evidence does not require that. Galaxies are consequences, not goals. They arise because gravity, matter, and expansion interact in specific ways. Their significance lies in what they enable, not in what they represent. They allow complexity to accumulate. They allow processes to repeat. They allow change without immediate erasure. From a purely physical perspective, that is already remarkable. There's also a practical aspect to their importance. Much of what is known about the universe comes from studying galaxies. Their light reveals cosmic expansion. Their distribution traces dark matter. Their evolution encodes the history of star formation. Without galaxies, the universe would be far harder to study. They concentrate information. They amplify signals. They act as markers across time and space. In this sense, galaxies matter not only because of what they contain, but because of what they reveal. They make the universe legible. As galaxy formation is traced from early times to the present, a pattern emerges. Complexity increases, but never without constraint. Stability arises, but never without change. Galaxies sit at this intersection, balancing accumulation and regulation over immense durations. Recognizing this helps frame the final stages of the story. Galaxies are neither eternal nor fragile. They persist for long periods, but they are subject to limits. Gas supplies dwindle. Star formation slows. Expansion continues. Eventually, conditions change. Understanding why galaxies matter also requires understanding where their influence ends. That boundary, where knowledge thins and certainty gives way to open questions, is where the next focus naturally turns. By this stage, much of the story of galaxy formation hangs together with reassuring consistency. Gravity gathers matter, dark matter shapes structure, gas cools, stars form, feedback regulates growth. Galaxies evolve within environments and change over time. The broad outline is stable, and yet important questions remain unanswered. Not because the framework is weak, but because nature does not reveal every detail easily, especially when events lie far back in time or involve matter that refuses to interact with light. One of the most significant unknowns concerns dark matter itself. Dark matter is central to galaxy formation, yet its true nature remains elusive. Its gravitational effects are measured with high confidence. Its distribution is mapped indirectly through galaxy motions, gravitational lensing, and large-scale structure. But what dark matter is made of at a fundamental level is still not known. This uncertainty matters because different forms of dark matter behave slightly differently, especially on small scales. Most models assume dark matter is cold, meaning its particles move slowly compared to the speed of light. This assumption reproduces large-scale structure well, but on the smallest galactic scales questions persist. Some simulations predict more small galaxies than are observed. Others struggle to match the detailed inner structure of dwarf galaxies. These tensions are not severe, but they are persistent. They raise the possibility that dark matter may have properties beyond simple gravitational interaction. Perhaps it is warmer than assumed. Perhaps it interacts weakly with itself. Perhaps multiple forms exist. Each possibility subtly alters how early structure forms. Experiments on Earth continue searching for dark matter particles directly, while astronomical observations constrain their behavior indirectly. For now, gravity tells what dark matter does, not what it is. Another area of uncertainty lies in the earlier stages of star formation. Population 3 stars, the first stars to ignite, play a crucial role in shaping early galaxies. They create the first heavy elements. They influence reionization. They regulate early gas dynamics. Yet they have never been observed directly. Their properties are inferred from theory and simulation. Models suggest they were massive, short-lived, and efficient at producing heavy elements, but details remain open. How massive were they on average? How frequently did they form? How strongly did they influence their surroundings? Small differences in these assumptions lead to different outcomes for early galaxy evolution. Observations of extremely metal-poor stars provide indirect clues, but they represent later generations influenced by earlier ones. The first stars themselves remain beyond direct reach. This limitation is not due to lack of effort. It is imposed by distance, faintness, and time. Even the most powerful telescopes observe the early universe near the edge of what light allows. The first stars formed in small systems whose light is easily overwhelmed or absorbed. Their brief lifetimes further reduce the chance of direct detection. Another boundary appears in the form of observational horizons. There is a limit to how far back the universe can be observed using light alone. Before recombination, the universe was opaque. Photons could not travel freely. No telescope, no matter how advanced, can see beyond that boundary using electromagnetic radiation. This sets a hard limit. Cosmic microwave background observations provide a snapshot of conditions at that time, but not before. Earlier phases must be inferred indirectly through theory, particle physics, and consistency with later observations. Even within the observable universe, distance imposes practical limits. Extremely distant galaxies are faint. Their light is stretched into wavelengths that are difficult to detect. Their internal structure is hard to resolve. Observations provide outlines rather than details. As a result, some questions remain unresolved not because they are ill-posed, but because available data cannot yet discriminate between competing explanations. This is where restraint becomes essential. In astronomy, it is tempting to fill gaps with speculation, to treat unknowns as mysteries demanding dramatic answers. The evidence does not support that approach. Instead, progress comes from acknowledging limits clearly. Dark matter is essential, but its particle nature is unknown. Early star formation is critical, but its details remain uncertain. Observational horizons exist, and they cannot be crossed with current methods. These statements are not weaknesses, they are boundaries. Scientific honesty requires stating where understanding is strong and where it is provisional. Galaxy formation theory is robust on large scales and over long times. It becomes less precise when pushed to extremes of scale, time, or resolution. This pattern is normal in science. It reflects how knowledge accumulates. Broad principles emerge first. Details follow slowly, constrained by measurement and theory. Over time, some uncertainties shrink, others persist, new ones appear. Importantly, the presence of unknowns does not undermine what is known. Gravity still behaves as expected, dark matter still shapes structure, galaxies still form through accumulation, feedback and interaction. The edge of knowledge lies in refinement, not reversal. There is also a cultural aspect to this restraint. Astronomy often deals with immense scales and deep time. Claims of final answers rarely survive long. The most durable progress comes from careful accumulation of evidence and willingness to revise models when data demand it. This attitude has served galaxy formation research well. Over the past several decades, the field has moved from uncertainty about whether galaxies could form at all under known physics to detailed models that reproduce much of what is observed. The remaining gaps are narrower, more specific and more tractable. They are challenges, not crises. Even humour finds a place here lightly. If the universe had revealed everything at once, astronomers would have run out of work long ago. Fortunately, nature is more patient. Another important boundary involves time itself. Galaxies evolve slowly. Many processes unfold over billions of years. Observations capture snapshots, not movies. Reconstruction relies on comparing different systems at different stages, rather than watching individual galaxies change. This approach is powerful but imperfect. It assumes that observed galaxies at different distances represent typical stages of evolution. In reality, diversity exists. Not every galaxy follows the same path. Some evolve faster, some slower, some take unusual routes. This variability complicates interpretation. Statistical methods help, but they cannot eliminate all ambiguity. Patterns emerge clearly, but individual cases resist simple classification. The universe does not offer tidy categories. Recognizing this prevents overconfidence. It encourages models that allow flexibility rather than enforcing rigid sequences. It reminds researchers that galaxy formation is a population-level process, not a single narrative applied universally. The edge of knowledge is therefore not a sharp boundary, it is a region. Within that region, confidence decreases gradually, explanations become less precise, assumptions become more explicit, language becomes more careful. This shift in tone is a feature, not a flaw. It reflects respect for evidence and for the complexity of the systems being studied. It avoids claiming certainty where none exists. It keeps theory grounded. There is also an important distinction between unknown and unknowable. Some questions may be answered with better instruments, more data, or improved models. Others may remain permanently out of reach due to fundamental limits imposed by physics and observation. Distinguishing between the two is itself an ongoing task. For now, many uncertainties in galaxy formation fall into the first category. They are active areas of research, constrained by data and guided by theory. Progress is steady, even if incremental. The presence of these open questions does not diminish the coherence of the story told so far. Instead, it frames it. Galaxy formation is understood well enough to identify where understanding ends. That alone marks a mature field. Standing at this edge invites synthesis, with the main processes laid out, with their interactions understood, and with limits acknowledged openly. It becomes possible to step back and consider the full picture. Not to resolve every uncertainty, but to see how much can already be said with confidence. From near uniform beginnings to structured galaxies, from darkness to light, from simplicity to complexity, the arc is clear. The final task is not to add new details, but to hold the whole story together calmly, without forcing conclusions beyond the evidence. That synthesis is where the journey now leads. Seen from a distance, the universe can look dramatic. Bright galaxies scattered across darkness, violent events captured in sharp images, immense energies released in short bursts. It is easy to mistake these moments for the main story. But when the full arc of galaxy formation is traced carefully, a different picture emerges. One defined less by spectacle and more by persistence, less by sudden change and more by accumulation. At every stage the same quiet forces return: gravity, time, matter. None of them hurry. None of them require precision timing or special circumstances. They simply continue to act, patiently shaping whatever conditions allow. Gravity is the first of these architects. From the earliest moments after recombination, it begins responding to the smallest differences. It does not need large contrast to operate. A slight excess of matter is enough. Over millions of years, that excess deepens. Over billions, it reshapes entire regions of space. What matters is not strength, but consistency. Gravity never switches off. It does not weaken with familiarity. It acts the same way whether matter is diffuse or dense, visible or invisible. It gathers, redistributes, and binds, provided time is available. Time is the second architect and perhaps the most easily underestimated. On human scales, time feels scarce. On galactic scales, it is abundant beyond intuition. Processes that appear ineffective over short intervals become decisive when allowed to operate for hundreds of millions of years. Changes that are invisible at first accumulate until structure emerges. Nothing in galaxy formation relies on speed. Gas does not need to collapse instantly. Stars do not need to form all at once. Galaxies do not need to assemble quickly. Given time, small tendencies dominate outcomes. Time does not force direction. It allows direction to express itself. Matter is the third ingredient and the most adaptable. In the early universe, matter is simple: hydrogen and helium drifting through expanding space. As gravity gathers it, matter responds. It heats, cools, compresses, fragments, and flows. As stars form, matter changes internally, producing heavier elements that alter its future behavior. Matter remembers what has happened to it. Each generation of stars leaves behind a chemical trace. Each episode of star formation changes how gas behaves next time. Over time, matter becomes more complex, not because complexity is favoured, but because nothing erases the past. Together, gravity, time and matter build galaxies without instructions. No blueprint dictates spiral arms. No schedule demands elliptical shapes. No final form is prescribed. Structure emerges because certain arrangements are stable for long periods under known laws. Disks persist because rotation and gravity reach a balance. Ellipticals endure because randomized orbits distribute energy evenly. Both outcomes reflect the same principles applied under different histories. Patience is what allows these outcomes to appear. If the universe were rushed, galaxies would not exist. Gas would remain diffuse. Stars would form inefficiently or not at all. Structure would be fleeting. Instead, the universe offers enormous spans of time during which small effects accumulate into large ones. This patience also explains why galaxy formation is uneven. Some regions gather matter quickly, others remain sparse. Some galaxies experience repeated interactions, others grow quietly. None of this requires explanation beyond gravity acting on slightly different initial conditions. The universe does not smooth over differences, it amplifies them slowly. Lawfulness underlies every step. There is no point in the story where known physics must be suspended. Gas cooling follows thermodynamics. Star formation follows gravitational collapse and nuclear fusion. Feedback follows energy conservation. Large-scale structure follows gravitational instability. Even uncertainty fits within this framework. Unknowns remain, but they do not sit at the foundation. They appear in details, in efficiencies, in timing, in extremes. The underlying laws remain stable across scales and eras. This stability is easy to miss because the universe does not repeat itself exactly. Each galaxy has its own history. Each environment imposes different conditions. Diversity emerges not from randomness, but from lawful variation. The result is a universe that is both predictable and surprising. Predictable in its broad behavior, surprising in its specific outcomes. Galaxies illustrate this balance clearly. Their existence follows naturally from known physics. Their variety reflects the immense range of possible histories allowed by those laws. There is no single moment when galaxies are born. There is no single moment when they are finished. Formation blends into evolution. Growth fades into maintenance. Change continues even as overall activity slows. At no point does the universe declare completion. This is why galaxy formation is better understood as a process than an event. The same forces that shaped the first galaxies continue to operate today. Gravity still gathers matter. Gas still cools where conditions permit. Stars still form, albeit more slowly. Feedback still regulates. Environments still matter. Nothing fundamental has changed. Only the balance of conditions. The present universe is quieter than its past, but not static. Star formation rates have declined but not vanished. Mergers are less frequent but ongoing. Chemical enrichment continues. Small systems still assemble. This continuity reinforces a central theme. The universe does not rush toward outcomes. It allows them. Even humour fits gently here. If galaxies were expected to meet deadlines, most would be late. What makes this slow-building universe remarkable is not that it produces complexity, but that it does so reliably. From nearly uniform beginnings, structure arises again and again under similar rules. Given enough time, gravity and matter find ways to organize. This reliability is what allows understanding, because processes are lawful and repeatable. They can be studied, modeled, and tested. Observations across different times and places can be compared. Simulations can reproduce patterns. Discrepancies can be identified and refined. Knowledge grows in parallel with structure. There is also a calming implication in this picture. The universe is not precariously balanced on rare coincidences. It does not depend on fragile sequences of events. It does not require constant intervention. It unfolds steadily. Galaxies form because conditions allow them to. They persist because the same conditions continue to hold, within limits. They change because nothing remains exactly the same forever. This perspective removes the need for drama. Galaxy formation does not need explosions to be interesting. It does not require mystery to be meaningful. Its power lies in accumulation, not surprise. By the time this process is viewed as a whole, individual mechanisms blur into a single flow. Gravity sets direction. Matter responds. Time allows outcomes to emerge. Nothing else is required. This synthesis does not close the story, it clarifies it. Understanding how galaxies form does not answer every question about the universe. It does not resolve all uncertainties. It does not point to final conclusions. What it does provide is coherence. It shows how diverse phenomena connect, how small differences grow large, how complexity emerges without instruction, how patience can be a creative force. With this coherence in place, attention can shift naturally toward reflection rather than explanation, toward what this long, steady process implies for the universe as a whole, not as philosophy, not as speculation, but as a simple recognition of scale, continuity, and restraint. The universe builds slowly, and in doing so, it builds reliably. That understanding is enough to carry the story forward calmly into its final reflections. From a distance, galaxies look like finished things, defined shapes suspended in darkness, spirals, ellipses, clouds of stars frozen in elegant arrangements. It is natural to think of them as completed structures, assembled long ago and now slowly fading. What the evidence shows is something quieter and more enduring. Galaxies are not objects in the usual sense. They are processes. They are patterns that persist because matter continues to move, gravity continues to act, and time continues to allow small changes to accumulate. At no point do galaxies truly arrive. At no point do they stop becoming. From the earliest moments after recombination, when matter was spread almost evenly across space, the same story has been unfolding. Slight differences deepened. Gravity gathered what it could. Dark matter shaped invisible frameworks. Gas followed, cooled, and settled. Stars ignited, altered their surroundings, and left behind richer material. Disks formed, mergers disrupted, environments influenced outcomes. None of this required urgency. Nothing needed to happen quickly for it to happen at all. Galaxy formation succeeds because the universe is patient. Over billions of years, processes that appear weak or inconsequential become decisive. Motions too small to notice reshape entire systems. Energy exchanged gradually redirects matter. History accumulates rather than resets. This patience is what gives galaxy formation its calm inevitability. There is no single moment when galaxies are born, just as there is no single moment when a river comes into existence. There is a flow, a continuity, a gradual transition from one state to another, guided by stable rules. Even now, galaxies continue to form. Small systems still assemble. Gas still accretes. Stars still ignite. Chemical enrichment still proceeds. The rate has slowed compared to the universe's earlier eras, but the process has not ended. It has only changed character. This continuity matters because it reframes how the universe is understood. Rather than a sequence of completed stages, cosmic history becomes a layered process. Earlier conditions influence later ones. Nothing is erased entirely. Each phase leaves traces that shape what follows. Galaxies embody this principle clearly. Their present structure reflects billions of years of accumulated influence. Their stars carry chemical memories of earlier generations. Their motions record past interactions. Their environments reveal the larger patterns they belong to. In this sense, galaxies are records, not records written in words or images, but in orbits, compositions, and distributions of matter. By reading these records carefully, astronomers reconstruct events far beyond direct experience. Yet even as understanding improves, restraint remains essential. There are limits to what can be known. Some details of dark matter remain unresolved. The first stars lie beyond direct observation. The earliest moments of structure formation are inferred rather than seen. These boundaries do not diminish the story, they define its edges. Acknowledging those edges is part of scientific maturity. Galaxy formation does not require final answers to be meaningful. It does not depend on solving every remaining question. Its coherence comes from how well-known processes fit together across vast scales of time and space. What emerges is a universe that is neither chaotic nor finely tuned to produce specific outcomes. It is lawful and permissive. It allows complexity where conditions support it, and simplicity where they do not. Galaxies arise because nothing prevents them from doing so. Gravity gathers matter. Matter responds. Time allows the response to unfold. There is something grounding in this simplicity. It suggests that the universe does not rush toward conclusions. It does not hurry to complete projects. It unfolds steadily, allowing structure to arise and persist without needing to justify itself. From within a galaxy, the timescales involved feel immense. From the perspective of cosmic history, they are simply part of a continuous flow. Galaxies form, change, and persist as long as conditions allow, then gradually fade or transform. Nothing about this process demands resolution. There is no final form a galaxy must reach, no ideal structure it must achieve. Spirals may become ellipticals, disks may thicken or dissolve, dwarfs may merge or fade. Each outcome reflects history rather than purpose. This lack of finality is not unsettling, it is stabilizing. It means the universe is not moving toward an endpoint that must be achieved. It is exploring possibilities within stable laws. Galaxies are expressions of those possibilities, not milestones along a predetermined path. Even the decline of star formation over cosmic time fits naturally into this picture. As gas supplies diminish and expansion continues, activity slows. The universe grows quieter, not because something has failed, but because conditions have shifted. Change does not require loss of meaning. Galaxies that no longer form stars still persist as structures. Their stars continue orbiting. Their dark matter halos remain. Their histories are preserved in motion and composition. Nothing is undone. Seen this way, galaxy formation is not a story of beginnings and endings. It is a story of continuity. The same forces that shaped the first galaxies continue to shape the last. The same physical laws apply now as they did billions of years ago. The universe does not reinvent itself. It deepens. This perspective also reshapes how observation is understood. When astronomers look at distant galaxies, they are not peering into a separate era disconnected from the present. They are observing earlier stages of the same process still unfolding nearby. Distance becomes time, but time remains part of a single flow. There is no privileged moment in this story. Every epoch participates equally. The early universe was not more important than the present. The present is not more complete than the past. Each moment contributes differently to the same ongoing structure. That structure is not fragile. Despite immense distances, enormous energies and vast timescales, galaxies persist. They absorb disturbances. They adapt to changing conditions. They carry history forward rather than erasing it. This persistence offers a quiet reassurance. It suggests that complexity does not require constant reinforcement. Once established under the right conditions, it can endure, adjust, and continue without needing to be protected or preserved. Galaxies do not need to be maintained, they need only time. As this long view settles in, there is no need to reach for conclusions beyond the evidence. No lesson needs to be extracted. No message needs to be imposed. The story stands on its own. Galaxies form slowly because the universe allows them to. They persist because nothing compels them to disappear. They change because change is the natural consequence of ongoing interaction. The birth of galaxies never truly ended because it was never a single event to begin with. It was and remains a process, one that unfolds quietly, patiently and lawfully across a universe large enough to let it happen.